at a data company. Don't tell anybody that. Yeah, Theo.
So Hetu is giving me a softball here because so many of the problems he talks about are at the core of the things that drive our work across all of the hats I'm wearing. At CZI with the virtual cell work, we're tremendously interested in building these very rich models of biology, ultimately with the ulterior goal to understand causal biology so you could identify which things cause disease. How are you going to think about controlling and intervening on cells in order to affect health outcomes? The difference is that we don't have a short-term path towards these things, but we take a long-term view, so we want to build richer models because this is pretty early. And this expresses itself in strategies where we think about characterizing, cells existing in the natural world by looking at cells that actually exist in organisms we see and how they behave. Then we have a very large-scale aspect of thinking about perturbations in an extremely rich way. We're generating 1 billion cell-size data sets in order to study perturbations of how cells will respond to maybe unnatural stimuli and unnatural things that we might not see in the natural world. Where you can think about this a little bit like in control theory, you first need to do system identification, then you can control a system. And we're thinking about it in this type of transition. And we're building generative models of the entire stack. And there's other fascinating work, like in an imaging institute, my colleague Alan Lowe is really deeply thinking about, and of course we collaborate on all kinds of things, but the inner structure of a cell. How do you need to look into not cells as bags of molecules, but really as structured objects where things interact spatially and temporally in order to affect certain things? And so we're kind of climbing our way on a very long time scale from these molecular characterizations of cells to these more spatial and structured ones, and ultimately to an organism scale. And the other side of it is, if you want to think about having identified what is the cause and what is the target, how are you going to actually treat these things, right? And at Akira, really think about simulation as kind of the tool to think about how can you get and design molecules that will be effective in order to treat patients. And there's this very rigorous, fantastic framework of molecular dynamics and simulations that has 50, 60-year-old ideas that have been translated to the environment where we apply multiple billions of teraflops more per available per second to these problems, and we're turning this all into machine learning and are trying to bring modern machine learning into the idea of how can we faithfully and with high accuracy generate and simulate molecules in order to actually go after the causes, to break through that bottleneck. And so I think the entire spectrum is very interesting to us, and we think that there's a bright future ahead for all of these problems.
Okay, thanks. So there were kind of 3 different themes that just emerged in some of the things you were talking about 3 pathways to improvement. So we heard about kind of like a physical understanding of what's going on. We also heard massive amounts of data to be collected, and then we'd heard about modeling or simulation. And those are all complementary strategies for advancing AI for science. Can you maybe talk about a little bit about the trade-offs between those? Is this just domain specific about whether you need modeling versus understanding versus data versus something else? Is it just where you are in your development life cycle? Do you need all 3? Can you talk a little bit towards, all of you, towards that kind of trinity of possibilities?
Yeah, I really like that question. So I think there's problems where we don't know how things work. And these are problems, for instance, all of this cell work, this is why it's still early, we just don't understand, quote unquote, the mysteries of the cell fully yet. We really need to generate and collect a lot of data in order to understand and build models and work in that space. And that's fascinating, it's a great time, we can get high throughput measurements these days and so on, and there's a lot to do. But there are spaces where we have knowledge about how processes work, and that's where physics is and simulation. And for instance, I think in these structured spaces, simulation and physics is almost a cheat code to think through them, because we know the physics of the world. We know, quantum chemistry, we know all of these things. And my colleague John has a poster here and can talk to you all about it. And in these domains, it's really important to be data efficient. You do not want to have to collect 6 trillion tokens before you can get a molecule. We're not going to collect, in a realistic drug discovery context, millions and millions of molecules that we test against something before it makes sense. We may need to do this with cells today in order to understand this endlessly complex microscopic object. But when we have physics and simulation in the loop, and we have all of this rigorous stack, we can cut through that with high data efficiency. And I think to solve that problem, it's paramount to reach for machine learning techniques that will have these data efficiency blankets. And so I think you need to adjust your approach to the problem. And this is what we're trying to do.
Other thoughts on that topic?
Yeah, I'll plus one Theo's point. I think my standard reaction is why not all three, right? But I think to Theo's point, I think different problems have both different constraints on how much you could throw data to the problem, or how much intuition you can add to the problem, or how much structure there is. In my opinion, as you go up to higher level models, as modeling higher level systems, if you're modeling atoms, there's fair amount of structure. Modeling physics, you're modeling chemistry. The laws of physics and the laws of chemistry are fairly well understood, are simple to describe. As you go up to things that are higher up, you tend to get more complex phenomenon, and you really need data to learn, because there's, in my opinion, not as much structure as there is, as modeling lower level atoms. So each of these is useful, but differently useful. And if I think of it, if I wear my learning hat on, ultimately you're trying to improve the model and you're moving gradient. And sometimes the gradient moves you towards more compute. Sometimes the gradient moves you towards more data. And sometimes the gradient moves you towards more structure in your models. And the general answer is a mix of all three, but some directions dominate at any given time.
Do you want to add?
I'll say a couple of quick things. I do think that what's interesting about this last point is that there are scaling laws for, say, natural language LLMs that we don't yet quite have for science. And that I think is sort of an exciting area. Can we actually understand the kind of the frontier on compute data and model complexity, which we don't, I think, fully understand yet. But the other quick point I want to make is I think sometimes these things are a bit counterintuitive. So for instance, in the protein structure prediction space, my intuition was that this is something which is very physical. We understand a lot about the underlying system, the underlying physics of the system. We ought to sort of bake in all these priors that can make us more data efficient. That was my intuition. It was completely wrong. Okay? Certainly in the case of AlphaFold, that's not how it turned out. The progression from AlphaFold 1 to 2 to 3 has been one of less physical priors, and essentially better ways of capturing information flow in neural networks. That was the innovation. I don't necessarily think this is a recipe that will hold in all cases, but it was in this case, and it very much sort of broke my intuition. So I think it's worthwhile to always be kind of skeptical a little bit about our own intuitions and how we tackle these problems.
Yeah, you want to say more? Or? Yeah, so I should say that for me, when I first got involved in AI for science, I made it my mission to try to make machines think like a physicist. And I wanted to make sure that the principles that I would teach a first-year student at MIT, conservation laws, and symmetries, that was going to be baked into those AI systems. And then some version of the bitter lesson is that actually it seems also important to teach physicists how to kind of think like a machine, and just the kind of things you can do just with quasi-brute force optimization, or at least guided optimization, is kind of amazing to me that you can make progress in that way. And of course, the hope, though, and maybe what was exciting, what you're saying about AlphaFold 3, is that despite the fact that you're kind of loosening some of the inductive biases, nevertheless, you're somehow getting something that's more generalizable and gives you some more physics base, even though that wasn't necessarily where you started. So yeah, please go on.
Yeah, the thing across all the fields of science, the thing that I've noticed is that in more cases, what you can do with AI for science is more limited by the data than by the model. That is to say, going across high-energy physics or astronomy, have these wonderfully curated data sets, all together, all interoperable, all that. Ecology has field stations all over the country taking their little data set doing this, and bring those together to the point that you can do transformative science, but you've got to have the ability to look at them together. So across our laboratory, the differences are, where is the data before you can start this? And some of the greatest successes, including AlphaFold, were on great data sets that they were trained on. And that's where the early successes have been. So something that needs to be done is, in a lot of these fields, a lot of work needs to be done on taking the data and turning it into a form that's interoperable and accessible and so forth before they can access these advantages. And so far, it's really a small part of science that's really in that shape.
Yeah, and I should say that this is a theme that hopefully will come up on the compute panel, that you can't just think about compute. You have to think about where the data is that you're going to do the compute on. And in some of the work that I've done, it's actually just been the egress and ingress cost of moving the data around that's actually been more of a bottleneck than GPU cycles. So let's continue on just this kind of abstracting of the lessons that we've learned. And so from the things that you've talked about, what are other abstract lessons, generalizable lessons? What actually works when we're doing AI for science?
Yeah, so I'll say for our lab, again, besides that data thing I said, the other thing that's really important, having AI machine learning data scientists on the one hand, and physicists, chemists, engineers, environmental science on the other hand, who are supported to be able to spend enough time together to learn each other's language, to learn each other's science, to learn each other's problems, and actually come to really deeply understand what they're doing. And if they have the time to do that and they're the right people, then they can do great things after that. But it takes some time to get started, and frankly, the way we support these projects have to be enough to give people that time. And research projects, the way they're funded by the federal government, don't always do this. I mean, we're lucky at our laboratory, we can use our little seed money, our laboratory-directed R&D, to basically put people together and start to work together. But that's where the biggest progress has been made. After those teams get some time together, then they can really do great things.
I'll come back to the AlphaFold problem because I think it's really interesting. I'm going to explain a slightly complex concept. I'll try to do it in less than 2 minutes, but just bear with me. So the problem there is, you have some cheap inputs, like let's call them A, protein sequences, and you have some expensive outputs, say protein structures. Let's call that C, right? And you're trying to go from A to C, right? That's sort of the high-level problem. In this case, however, there's just not enough data, and this is true for many problems in science, right? We have maybe 100,000 protein sequence structure pairs. What AlphaFold 2 did, right, was find an intermediate B, in this case, these sort of notions of MSAs or multiple sequence alignments. I won't go into it, but just think of it as sort of an intermediate type of data that is a lot cheaper than C, a lot cheaper than structures, and it's very easy to get, almost as easy as A. And what they did in that case, and this is why I said they kind of cheated, is they did not solve the A to C problem. They solved the B to C problem. Right? They took this intermediate kind of data and used it to train a model that can go from B to C. Now, once having done that in AlphaFold 3, then they used this sort of approach, the previous model, self-distillation, to generate lots and lots of C examples, which they can then associate from A to C and actually solve the initial problem that they tried to solve. Right? And I think this idea that there is some sort of cheap data or there's some sort of intermediate construction that you could use to solve a preliminary problem that then helps you go solve the initial, the harder problem is really interesting, and I suspect will show up over and over again in science.
Interesting.
When Mohammed made his previous comment, I was going to interject. I was almost tempted to interject, but now he's completed the story, so I feel better. But I love the ideas. I love the theme so far. I'd say to add to that, there's a few things. So, the obvious thing, if you're a computer scientist coming into a field like this, is you look at LLMs and there's a leaderboard and there's an eval set and people move things. And the first thing somebody who joins my team says, well, what's your eval set? And we're like, we're making one, hold on. And so I think understanding the ways to objectively evaluate the problems and even agreeing on them is a surprisingly non-trivial problem. Maybe because of the breadth of problems that we're trying to solve, maybe because it requires multiple disciplines to interact together to agree on something. And I'd say we spent the better part of a quarter in the company just agreeing on eval sets and establishing them so we know when our models are getting better. In structure prediction, it's nice because you have a clean data set and everybody's agreed that there's a nice eval. So that's one general thing, being able to evaluate progress. Data to train models obviously is the other generalizable thing. I'm not saying anything surprising there. I think the third thing that we've seen, and AlphaFold 3 was an example of this, is the use of test-time compute. I think I met somebody on the way in the morning and I was like, my inference bills are blowing up, but at least the models are doing well. So I think test-time compute has helped us get more out of less. We are all at the end of the day, a data scarce regime, and some of these innovations in the AI field have meaningfully helped us bend the curve there. So these are things that I'm excited about. These are hopefully generalizable, and we'll see how it plays out next year.
Wow, everything has been said. No, let me, maybe what really works, the distilled version for me is one, cultural, and then there's technical aspects. And the cultural aspect has been mentioned, but I think it bears doubling down on. There's a lot of prior knowledge, you were talking about this, that people have that they really want to bake into their problems. And the history of machine learning in any application field is coming in there and making people who stick to that feel like dinosaurs a few years later. And I think that's just something we really, really, really have to embrace, as uncomfortable as it is. Because the uncomfortable aspect of this is that our ideas that are interpretable to the human mind are not the right ones. That's a very, very tough lesson. That's why it's bitter. It's a hard pill to swallow. But there is absolutely tremendous amounts of value and knowledge and depth to this domain knowledge. So how do I think about this? This is why I'm saying it's a cultural thing. I believe successful teams in AI for science have to be composed by people who have understood that lesson and go all in into learnability and, so to speak, empirical risk minimization. Understand that the thing you're doing is subject to learning rules. There is no such thing as a right model. There's just models that are more predictive or less predictive. And that's the only thing you can rely on. And the only thing you can do in life is validate whether they're right or wrong on certain areas by doing experiment later on. You're not going to learn the right model. That doesn't exist. That's a fallacy. And pairing these people with domain experts who can really explain to them not to do extremely stupid things like overfit errors, overfit the wrong experiments, overfit to the wrong, entirely wrong objects, right? So I think understanding the problem shouldn't be the thing that makes people design these handcrafted solutions anymore. That's the past. It should be so that people don't make mistakes in fitting irrelevant quantities and trying to build irrelevant models. So I think those two need to be attached to the hip, and that joint culture will create solutions that we've seen in all of the examples that have been given that will go extremely deep. So machine learning shouldn't be something we pepper on top. It needs to be part of the process from the beginning. And by that, I also mean data generation. So this is the second aspect I want to say, which is partly also cultural, but also technical. Something that really, really works is to throw away the idea that you can come in with machine learning later on. It's a machine learning problem beginning to end, and actually I think we should throw away the term machine learning or AI. It's an information problem. The only thing that exists is bits of information about the world. And how do we get them? We get them from experiment, observation. We get them from intervention, which is also an experiment, and we get them from processing information through information processing systems that transform this into intermediate quantities or final quantities or whatever you want. And if you don't design your experiments with that thing in mind, you're going to design the wrong data that flows into the wrong systems, and you will be stuck with conclusions that are not particularly great. So I think embracing this means your data strategy becomes your model strategy. And that's also an outcome of the bitter lesson. And that's also what we see happening in the commercial LLM space and everywhere else. So I think seeing the entire thing as one stack is eminently important.
Very cool. So we heard a bunch of different things about what works. So when we talked about kind of teams and the cultures around teams, we heard about having appropriate benchmarks, also thinking about building kind of end-to-end the way that you're going to go from data to model. We heard about test time compute, which is another kind of new knob that we have. You know, one thing that I'm curious about is kind of on the understanding end of the spectrum. I was mentioning already in my own work, kind of teaching myself kind of how to think more like a machine has been helpful. On the other hand, in the curiosity-driven regime that I'm in, it's not just about discovering some compound and being able to test that it works in the way that you want to. Actually, gaining understanding is kind of the fundamental objective. And so there also is that kind of tension for those of us who really do want to have understanding and human understanding as our goal. And yet, I think it's actually entirely true that you need to, in some sense, train a new generation to think about problems in a different way. And Boris and I were at a workshop that was happening at MIT talking about AI plus science and the future of that. And one of the things I brought up was that of kind of building centaur scientists who have the domain knowledge, but are not limited by the domain knowledge and know how to incorporate machine learning strategies in a synergistic way. So these are a lot of abstract lessons. Any responses from the panelists to what your fellow panelists have talked about? Yeah.
I'd like to pick up on what you were saying. Yes, on the centaur scientists in particular. And when new technologies and techniques are brought into science, frankly, most of it is done by young scientists, by graduate students, by postdocs, who grow up learning, thinking this way. So you say, what am I worried about looking forward? One of the things I'm worried about is bringing those scientists into the fields. I'm at my laboratory. We have 500 postdocs, and they usually come there with one set of background, and they go out to wherever they go with a completely different background. That's what they were doing. And in this case, they're learning how to work these things together. Well, we're doing this at a time when physics departments, I know, are taking fewer graduate students, where people are in this country are looking at where am I going to get the best opportunities to pursue this in universities, and are looking abroad. And so I say, what's the challenge? I think it's the broader challenge for science, because in the end, it's that junior people in the field, bringing the brightest people into the field, is what makes progress.
Right. Other comments?
Yeah, maybe picking up on a couple of points here. I will say I like the phrase centaur scientist. I noted it down, and I'm going to steal it from this panel.
But just as a side note, if you're going to use it, there's this amazing New Yorker cartoon about the centaur scale. So you can look it up right now. And so a colleague of mine sent this New Yorker cartoon to me, and it actually represents, in some sense, the tension. So you have there's like too much human and too much horse, and that's not effective. You need to have just the right amount of horse, that right balance. And so if you find that cartoon, I'd recommend using that for talking about centaur science.
A phrase I did not expect to hear today, just the right amount of horse. But centaur scientists I'll keep in mind. I love that. I had this phrase, digitally native or AI native scientists. That was good, what I was going to use, but I like the word centaur scientist better. I think one of the things that I am seeing, or we are seeing, is, we are getting the latest generation of students coming out of school are just, thanks to the people training here, are just amazing. I mean, you see these physics majors, these chemical engineers, these chemists, and they know everything that's happening in the AI world. They're writing code thanks to Copilot or whatever, non-trivial code. I just interviewed someone who has who's graduating with a Bachelor of Science in Chemical Engineering and has written a CUDA kernel. Half the hardware engineers I've met haven't written a CUDA kernel. So it's just amazing to see how this excitement in AI and this momentum around AI is lowering the activation energy for everybody else to become essentially AI native. And I think that is a great harbinger for the future. I know there are challenges, but I think that's the positive I'd like to harp on.
And maybe I want to pick up also on this idea of the centaur scientist and understanding as terms. I think the word understanding is simple and appealing, but it really is always contextual. Our understanding is always contextual on our assumptions and on what else do we think a priori needs to be true for me to qualify something as understanding. But machines don't think this way, and nature doesn't care about our assumptions, right? So I think we need to remember a little bit what is science. Science is you keep hypotheses while trying to reject them. You're not trying to predict the right one, you're trying to reject them. And only the surviving ones are true, which is how I'm trying to think about we need to make our models better and better and better and better and better, and understanding is always contextual in the assumptions we've made. Let me give you an example. There's an abstraction layer in everything we all do. I believe I understand my car when I push a button and it goes forward, and that doesn't mean at all that I understand every single bit of it all the way down the line. Similarly, lab scientists, I know these days they use kits, they use all kinds of things, and maybe it would be crazy for them to go all the way down to synthesizing everything from the beginning. So abstraction is the magical tool that we can use for higher level understanding, which also changes the term of understanding. So I think we should think about abstraction and contextual understanding a lot more than in the absolute terms in order to allow ourselves to be happy with our progress.
Yeah, please.
Just one quick follow-up. So I completely agree. And I think one thing to sort of note here is I don't necessarily think that physical phenomenon are all amenable to sort of human understanding by a brain, by a human brain. Right? So physics might be, but biology may sort of fundamentally not. I think the notion of abstraction is critical here, and so one sort of has to make some compromises in a way in the level of resolution which we can understand something. But it may be able to be the case. So there are certain types of physical phenomenon, including biological one, that are just so complex that no human, at least with sort of our kind of 2025 brains, can really grok it in a way that similar to how we understand physics at this very fundamental level.
Yes, so actually physics is a great example of a little bit of a duality. So the physical laws at the kind of fundamental scale are quite well known. The standard model of particle physics, we have Einstein's relativity. Of course, there's challenges of putting those two things together. But when you actually go and try to make physical predictions, you find yourself oftentimes in a regime where there isn't actually a good summary description of what's happening. So for example, 10% of all open supercomputing resources in the United States are used to solve the equations of quantum chromodynamics on a lattice grid. And there, you're trying to understand nuclear structure, and you can do the nucleus of hydrogen, helium, maybe lithium, beryllium, but you're kind of running out of steam already. And so while the fundamental equations are known, actually you find yourself unable to convert those fundamental equations into predictions. And so Mohammed, one of the things that you mentioned is kind of coming up with these more like intermediate representations or constructions. Do you view that as just a pathway to go from A to C? Or do you view that as a pathway to actually kind of understanding the way that a system works at some level? That is, when we're doing abstraction, is it abstraction but also hierarchical abstraction so that we can really think about compositionality? Or is it something else? Can you say a little bit more about your thoughts about kind of intermediate steps in learning?
Yeah, I think it's both, in a way. And let me go back to the example I got helpful. So, what was interesting in the kind of the B2C example is that it was sort of there was not really an understanding there, but it was sort of useful. In the way that a microscope is useful in sort of giving you images, right? So it's sort of, you can use it to make hypotheses about the biological system, but it doesn't necessarily teach you or tell you how that process is happening, right? Then in the second case, right, where we went from A to C in AlphaFold 3, then I think we've actually gained physical understanding. Now, in that case, so that physical understanding, I should say, is embedded in the model. It's not necessarily something which we can sort of look at and decompose and understand individually, but I think the model has sort of internalized that understanding. And then that's also even more powerful, but also just more general. So you could actually make predictions that are more out of distribution than you would otherwise.
Mohammed, so would you say that a test of understanding from a model perspective, not human understanding, is essentially its ability to generalize out of distribution to places where, the same laws must hold?
Yes, I would say so. Maybe it's slightly differently framed, is at least it sort of converts a problem that we care about into an in-distribution one. Right, so at least given a data set that we have, or given whatever sort of methods that we have, suddenly a problem that sort of was previously out of distribution, now it becomes in distribution. And if that happens, then I think we're good.
So in this, what you're saying is not everything can be easily understood by a human in a way that they can give an easy narrative. And so we have to get beyond that. But there still is the point where you have to be able to validate it to domain scientists in that field who do not know AI. And that's the hard part about AI in science as opposed to other things, is that the standard, that in the end when that paper goes out, the scientist has to say, I believe in this, I've trusted this, I know this. And I think that's something, I think we're going to see some of this tension as we, going forward, of cases of getting a lot of pushback about whether this is really science here or is just a model doing its own thing.
As a concrete example, for an eval set, there are cases where someone says, ooh, Jesse, I've done better than your model at achieving performance on something that you thought, Jesse, you were the smartest person on, but I found a model that does better. And I say, okay, maybe by the criteria of that benchmark, but I'm concerned about other things, and it's hard for me to articulate exactly what those concerns are. I'm concerned that somehow you're really not getting it, or maybe there's something wrong with the benchmark data set, or maybe there's a systematic, or there's something. But as a scientist, I have a hard time articulating it in a way that I can then convert into a number. Yeah. Hey, did you want to say?
I was just going to add, maybe to establish a parallel which might appeal to this audience. If you go back to when quantum physics came out, right? I think you could have made many similar concerns. We don't understand it. It doesn't make sense. It defies intuition. Today, we don't disagree that that is the more accurate representation of the world. So I think essentially what we're doing is, in some aspects, in some places, we're moving from mathematical equations that describe the world that we didn't understand and that new generations have learned to understand and intuit, to pieces of code or AI systems that understand it. And hopefully the next generation of scientists will learn to build intuition based on that. But at the end of the day, you need to do an experiment and show whether it understands something or not.
And I think you we've heard a few of these challenges about how to connect with domain experts and scientists. And ultimately, I don't think this is just about communication, it's about value. How do you show your crazy model that is eminently wrong because it's just some millions, trillions, billions, however many parameters? That's not nature, right? It's just some predictive system. How do you show this thing as value? Value doesn't just come from, here's my benchmark, I trained it, it minimized loss, I'm happy it's better than your handcrafted equation. So I think we really need to work extremely hard as a community to do one thing that is the only thing that will convince and communicate with domain experts, which is the following. I do not think we should get to the point that we try to make machine learning look exactly like what the domain experts are used to seeing. That is the wrong approach. That will not succeed. That's not fish, it's not meat, it's somewhere in the middle, it doesn't work. What we do need to do is we need to really force ourselves jointly, writ large, to think about systems and applications and use cases that we find valuable, where we say, I really want this system to behave the way I want it to behave. Can you show me your thing can do that? And then you do that. And you leave the how to the system. That doesn't matter. So I think, and that is not exactly benchmarking, that is really downstream use cases where you can demonstrate value. And I think that idea of downstream use cases with value is very, very difficult. It requires a tremendous amount of discipline, but we really need to think in these terms in order to measure, in some sense, and validate whether our machine learning makes sense or not. And to me, that's, you asked us to think about this later on. To me, that's a big gaping hole in most of AI for science nowadays. We work on benchmarks, we work on fancy numbers, we work on systems that we say, hey, I can interpret this by plotting some U-maps, which is horrible. But what we don't do enough is really have the end-to-end link to really use cases where we can demonstrate, because that's hard in the sciences. It needs lab work, it needs physical experiments, it needs things like making a material, making a drug, it needs the reinforcement all the way back. And this is why, for instance, tech has been so successful in applying machine learning, because they can do A/B tests. They put it into their products, they get feedback from the world, they see it produces value for them, all the way through to the thing they care about, which is maximize dollars. In science, that feedback loop is sparse and delayed. It's very hard, and I think that's what we need to work on.
Right, so a great transition into the obstacles, and so going from the optimistic AI for science, wonderful breakthrough research, now to some of the challenges that you face. You mentioned already kind of the challenge of showing value, especially to scientists. Before 2016, I was very much an AR curmudgeon. I basically said, none of this machine learning, don't do any of this deep learning. I'm a theoretical physicist. What I do instead is I do deep thinking. I was the kind of person who was kind of fighting against the growth of AI. And now an example of the type of fight that I have kind of mentioned already is that some of the incentives in AI for science aren't necessarily aligned in the right way. That if you can get your bold-faced line in a NeurIPS submission, then you're like, great, I got good performance, but the performance benchmark isn't always the right one, where for physics applications, oftentimes you care about systematic uncertainties, you care about proper uncertainty quantification, and it's hard to explain to someone that if the uncertainty is bigger, but more correct, that's better than a model that gets better performance, but the uncertainties are not estimated properly. So kind of incentive structure is an example of an obstacle that I faced in my domain. So maybe we can talk about some of the obstacles that your field have faced. It might be logistical obstacles, it might be conceptual obstacles, and even ideally, if you have any ideas about how to mitigate those things, and maybe get advice from the audience about how you might overcome some of those roadblocks. So Mike, you want to start?
Yeah, so I'll go in a different direction, which is are results from AI accepted by society, even though they're based on science? So this is going to be important. So I'll give you an example, weather prediction. There are models that can predict weather better than the European model now. And what they're particularly good at is giving quantitative estimates, the probability of a really catastrophic rainfall in this little area. Okay, now you would like to use that information to be able to improve. So if you're going to have to get people out of that area because it has a 4% chance of a catastrophic flood, is a pretty big probability. You have to get people so now do you tell people that that's an AI-based production? Does that mean that they'll believe it or not? I mean, this is, in a lot of the earthquake predictions, other things like this where you're actually using this for society, there's a lot of understanding. How do you talk to people about this? Are they going to trust it?
Great. Mohammed.
Sure.
So I'll give one technical and one sort of logistical problem. So the technical, I think, is that we've picked a lot of low-hanging fruit, or we are making our way through the low-hanging fruit, and I think pretty soon we're going to enter domains where there's just very little data, or the data is very, very expensive. And I think we might actually see a bit of a surprising slowdown in our progress once we've gotten there. And so that's something that worries me a little bit. And I think it crisscrosses across many domains. I can talk about biology and molecular biology, but I think it's true in other areas. The other, somewhat related to this, but more of a logistical point, is that it's actually hard to generate certain kinds of data sets. Ones that are pretty basic in the sense that their use case or their value is not going to immediately translate into a company or a commercial product. But at the same time, it's not sort of exciting enough from a novelty perspective that a federal fund, if federal fund that still exists, will actually go give you money to do it. Right? So there's this sort of in-between type of data that I think is incredibly valuable for building next-generation machine learning models and just better understanding of these sort of systems. But that's actually really hard to get off the ground right now, and that's a missing middle.
Yes, I'd say data remains a challenge. Being efficient with data is something that we're getting better at, but I completely agree that we are hitting bottlenecks. So that will remain a challenge, at least for the scientific disciplines that we care about. Sometimes we are dealing with ends of dozens, not even ends of millions or thousands. And what do you do with it? You have to. You still want to make progress on the problem. The second challenge is maybe cultural, which is we are getting a lot of these people together to work together on a problem, but maybe what Theo was suggesting or alluding to is it takes some time for us to learn to speak the same language and for us to build trust in the models that we're doing. So that's kind of why I started with evals and understanding, what would convince someone. It's not simply an LLM leaderboard. It's basically what would you see which would convince you that this thing is real and that we are making progress. And sometimes agreeing on that and getting to that set of experiments or data or metrics is the hard problem. Sometimes you do that, you achieve it, and then you realize, well, there's still a gap. So coming to Jesse's point, I mean, yes, it's doing better in the benchmark, but is it really better? Here are the 5 other things that I'm worried about that we hadn't considered before. So I think those two, the technical data and sociological or cultural, which is building trust in a system that changes by the day or by the week, remains a challenge.
Yeah.
So there's a cultural problem that touches on resources, and I want to expand on that in a way that maybe hopefully doesn't sound backwards. Everyone has said we need more data. Eminently true. I think that there's a little bit more to expand on that. We need more compute. Absolutely true. A little bit to expand on as well. And we need people who are trained and speak languages and can communicate. Absolutely true. But I think what we really need to see what's underneath all of this is this professionalization of science. If you mentioned it already earlier, right? This idea that we have an LHC now, it does large-scale experiments. That is not the same physics some professor did in their lab by themselves with their 3 grad students. It's a very different scale of object. And whenever we transition to a field getting to the point where you need a lot of resources to do a thing, you need to think about it very differently than in this very grassroots type of way. And that has repercussions that are deeply uncomfortable for everything we're doing. Let me start with the data. One could say, if we only funded enough labs to generate enough cell data, we would have all the cell data in the world and we would be great. And I would postulate right now, no, that's pointless. Not because funding is bad, I don't want to get into that at all, funding is great, but because data sets that are useful for machine learning need to compose into a metadata set that you can weave together, they make sense, they have been designed with a coherent experimental question in mind. There is no such thing as data set generation that is free of a theory, by the way. Every time you collect data, you make assumptions about it. It doesn't matter whether you know them or not. And most of the data, let me give you an example, in cells of all types, it's so incoherent, it's so noisy, it's so inconsistent, and it's typically an N of 1, where people say, I just want the data to write my Nature paper, leave me be. But if you want to build machine learning models, you need replicates. You need to be able to disentangle what is aleatoric uncertainty and noise. So what is the instrument doing versus what is the biology doing? What are all of these effects that are coming together? And you need a very professional data set generation strategy at high scale, probably with simple systems that look very boring, where you can control a lot of variables in order to create very controllable large-scale things, in order to dig into questions that sounded different. For instance, asking the question, what is transcription factor 33 doing, is probably the pointless type of question to generate a data set for in the age of machine learning. You could ask a question in general about a system and about how things behave and generate rich data sets for, and then ask that question as a predictive one of that system. And over time, as your models get better and your data sets get deeper, you will be able to answer hundreds of those, not one. And I think that transition into this team science, professionalized science, where we think about resources and we have a plan and we pre-register these plans and we generate data sets coherently and we plan out the compute, that is something academia is not set up to do at all. And we really have to come to terms with that in the AI age, with these gigantic systems that are very expensive and laborious to build, it's pointless to build little things beyond exploration to show that something kind of works. But for big science, that's not the way. So how do we go about this? And we need to really think about this hard as a community.
Yeah, and it'll be interesting to see kind of the timescales for this. So if you think about particle physics in the Large Hadron Collider, there are these incredible planning exercises that happen. Or if you're going to launch a telescope into space, like you're basically, there's winners and losers, and you're saying things get funded and who doesn't, and you have to coordinate as a community. And particle physics is a little bit unique in that we have done this coordination. And I was horrified to hear that in certain areas of material science or in chemistry, if you want access to the data, there isn't just a place that you can go for the data, that you're scanning through whatever journal articles and probably behind paywalls. Whereas in high-energy physics, we have HEP data. So there it is, all the histograms, there they are. And so, but you can ask what drove that cultural change. And I think in particle physics it was because we had to, because there was no way of doing a tabletop particle accelerator. Well, maybe you're going to build me one eventually, but
the data will still be a problem.
That's right. Do you want to respond?
Yeah, well, no, I was saying exactly. So I've spent most of my career in universities, and I was a vice chancellor of research at UC Santa Barbara, and I've been director of 2 national laboratories. They're both outstanding research institutions, and they're really different. And part of that is exactly the way you said, and part is what is incentivized. To have this interoperable, large managed data sets for the long run for the community, people in universities do not get tenure on that basis. Let me be clear. It would be great. But in some sense, even in the high-energy physics, that's sort of how laboratories came to be. We're doing things like this, who can be the steward of this for the long run. And so we have that in high-energy physics. We have that in nuclear physics. There are a lot of fields of science that need that, who don't have it right now. But there has to be some recognition that it actually costs money to do it. And so some fields have not quite taken to the point that you actually have to charge extra money just to do the curation of the data. You just do that on the side. Universities are expected to just do this on the side.
So the other thing that came up was trust, both trust in terms of the science that we do, communicating that to society, but also a little bit about kind of the trust between scientists themselves. Do you have ideas about how to help that? For example, if I have an AI-enabled drug discovery, do you tell the public that that's how you came up with that drug? Is that useful? What type of education does the public need? Or similarly, if you're telling a scientist, hey, I'm going to invest in a particular AI-driven strategy as opposed to a more traditional strategy, that actually is a good investment of money. Do you have ideas about how one might address the trust gap?
Yeah, I can take that. I have got this question a few times. There's the easy answer, and then there's the more nuanced answer. Well, in specific to drug discovery, we believe there still is a well-regulated system to evaluate the safety and efficacy of a drug. And it doesn't really matter where it came from. We have clinical trials, we evaluate risks, we evaluate efficacy, and that's ultimately what makes a drug approved. So that's the easy answer. There is a path. We have a well-understood to evaluate the molecule, and that should hold. But I think the more nuanced answer is that even if I convince you, there might still be skepticism. And that skepticism in today might come from the fact that it came from AI, but tomorrow might come from something else that reflects a lack of understanding by the general public of the deep science involved. And so how do you build trust in the general public for the experts who've really thought through this is probably a problem many of us face and continue to face. And I think the AI version of this is just the latest instance. I don't think it's a new problem.
I think it's even like in human relationships and in everything else, the elements of trust are consistency, transparency, and value. And I think if we unpack that to science and to AI, consistency means it does what I say and I say what it does, and that is kind of always there. If we use the system today, make a prediction, it will make a similar prediction tomorrow. We have this kind of flow, and when we update the system, it's not as if everything was wrong, but there's detailed changes. Let me give you an example. People were using stable diffusion. This was one of the early image generative models. People used this for their creative endeavors and so on. And at some point there was an update, and they did all of this prompt engineering stuff, and they found out exactly how to make these things create exactly the type of assets they wanted. And then Stable Diffusion 2 came out, and nothing worked anymore. All of the people had taken their professional endeavors to say, I will be creative with this thing. Their entire workflows were ruined. It ruined trust. That product was dead. That is the thing about consistency. Consistency is extremely important. Then transparency, we need to exactly show what's in it. As scientists, we need to exactly say, this is in it, this data set, this is the method, this is the thing. So you need to be crisp about communication and not hide anything, right? We need to be very, very professional about that. And value is what we talked about earlier, which is people need to see what this thing can do, and it needs to prove itself around use cases. I think if we get all three of those right, we're giving our communicators a lot of material to go out and talk about this in very simple terms and try to build trust with the community.
Add one more point, which is, at least for communication with scientists, not the general public, I think blind challenges could be a very critical component of this, right? And this has been true in the case of protein structure, actually, where historically the field had many, many problems, some intentional, some unintentional, where people claimed certain results that just didn't prove to be true, and it took essentially the development of these blind challenges where people simply cannot cheat, where you're essentially submitting these predictions in a way where you cannot control how that assessment is done. Essentially, even the metrics were sort of hidden from you, and that process is ultimately what really led to sort of sustained development and growth in the field. And that problem is very kind of well specified, so it wasn't amenable to this. But I suspect there are many areas of science where we could do similar things.
Mike?
This issue of trust in science is very essential. It covers here, but the National Academy of Sciences is spending time on this all the time, how difficult that is. If you think about fields such as what happened to GMO products, okay, it basically got on the wrong side of that communication, and even GMO products that are very safe, in fact, can't be sold in whole countries because once it got off in that corner, they couldn't get it back. We do have to think about that in AI. It can get into that corner where you can't get trust back. And so that's something that everybody working in this field has to realize. Every time somebody goes and say, oh, well, yeah, I use this thing, and I didn't get the answer I wanted, so I changed my prompt a little bit, and then I got what I wanted. So you have to think about what that means to them about what AI is really like in science.
So we're coming close to the end of the hour, and we're going to have the great research posters and lunch coming up next. But we've covered a lot of ground already, but I just want to see, are there any last words, 30 seconds each? Are there something that you want to emphasize that's already been said on the panel, or something that hasn't yet been said that you want to make sure that you surface? Mike?
I'll just say I have many of my colleagues from Lawrence Berkeley Lab are here. Go tell them, and you can find out a lot more than I was able to tell you.
Great. Mohammed.
I know funding is going to come next, but I just want to kind of mention, people might not be, I think people are aware, but just want to communicate the seriousness of this is that the funding situation currently is really quite dire, right? My group, many other groups at Columbia, at Harvard, and elsewhere have essentially lost all their federal funding, right? And I think this is critical, not just for the academic research we're talking about here, but also the pipeline in terms of students and people who are trainees who would come into your companies and so on, trained to be trained well enough to actually be able to do research from day one, right? So if we lose that, I think the whole ecosystem will really collapse. I don't have any solutions, but I just want to kind of communicate the seriousness and gravity of the situation.
Slightly related, maybe I'll just remind everybody in preparing for this, I was thinking about it. We are saying AI for science. I think we forget that AI came from science. Are the founding people who built the foundational models and the innovations in AI all were scientists by training. Joshua was a physicist. Jeff was a psychologist by training. So again, I think it's basically AI is the developments in AI that are helping science came from scientists in scientific disciplines. And it's important to remember that when we're thinking about the funding situation for things that are doing AI, but also not doing AI, because you don't ever know what the next AI will come from. So,
now on that front, I would just say exactly, this is all science. There is no, this is engineering, these are elements of science and of creating knowledge in the world. And the last thing I want to say is just selfishly, John is here, John is my co-founder and the world's best person to talk to if you want to learn about biomolecular simulations, and he has a poster up there, so you should spend time with him. That's all I have to say.
Great, so let me just reiterate the points that were just made at the end here. Today is a celebration of AI for science, but as you mentioned, science or AI comes from science, and it's not just it came from and it's over. It's that it's continuing to happen, and that we should just be reminded that science offers both extremely challenging problems that can drive AI innovation more broadly, but also scientific methodologies are ways to actually understand the way that AI systems work. And so we shouldn't just think of ourselves as consumers of AI, taking what's coming off the shelf. We should be really thinking about ourselves in some sense as co-developers. But again, today is a celebration of the scientific outcomes that we're getting from this, and really excited to go next door to the posters and see other great advances that are happening in this space. So thanks to all the panelists, and looking forward to your engagement, and looking forward to a wonderful rest of the day. Thanks very much.
Before we go over to the posters, let me just say thank you to everyone on the panel again for coming. This has been super insightful. I think in my mind, I think of the great John von Neumann, who once said, you don't learn mathematics, you just get used to it. I think that speaks to some of the cultural kind of issues. And so hopefully we'll get used to the new way of doing science through the poster session and the kind of lunch provided.
Check, check, check. Check, check. Good.
Please play responsibly. Must be 18 years or older to purchase, play, or claim.
Oh, I'm so sorry. Everyone, lunch is also being served in the back room for whenever you're ready and hungry.
Check,
Hey, hey, hey. Hey, hey, hey. Check 1, 2. Hey, hey, hey. Check 1, 2. Hey, hey, hey. Check 1, 2. Okay. Why can I hear the people? I can hear them. Is the mic on? Hey, hey, hey. Check 1, 2. Hey, hey. Okay. Check 1, 2. Okay. Check 1, 2. Hey, hey, hey.
evaluating potential hires for your small business, it's essential you look beyond resumes. Sure, a candidate may appear impressive on paper, but understanding the person is crucial. LinkedIn, the world's largest professional network, provides a complete view of your candidate's skills, experiences.
hey.
Hosting season's here. Are your Windows guests ready? Early access to Blinds.com's Memorial Day mega sale is on now.
Just a quick announcement, everyone. We're going to start again in 2 to 3 minutes.
Check. Hey. Hey. Check, 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 check. Check, check. Hey. Check, check. Check. Check, check, check. Check. Check, check, check. Check, check, check. Check, check, check. See, hey.
Okay, we're about to start the panel on funding, so can I please ask all the panelists to come up to the stage and all the people in the audience to come and take a seat. There should be one more. Worst case scenario, there's more time for you guys to talk. Yeah, I think that's okay. Okay, welcome back to the afternoon session. So our next panel focuses on the role of infrastructure, data, and models in AI for science. And we're thrilled to have Jared Quincy Davis as our moderator. Let me very briefly introduce Jared. So Jared is the CEO of Foundry, which was founded to radically bend the curve on GPU cloud economics, to restore the elasticity promise of the cloud in the GPU context, and to democratize the tools, abstractions, and leverage previously exclusive to labs like OpenAI and DeepMind. Foundry is proud to be an infrastructure partner to many of the frontier builders in this room. Prior to Foundry, Jared was a research scientist at DeepMind and Google Brain, where he was happy to have all these things provided to him. So Jared, like many others on the Foundry team, sees enabling builders in this category as one of our raisons d'etre. And yeah, I think we'll learn a lot about compute and data in this context. Please, Jared.
Awesome. Thank you, Boris. Well, thanks everyone for coming. I think it's been a pretty exciting and stimulating day so far. And this panel, I think, will add to that. We've got a pretty amazing lineup of great people, many of whom I've known for a while and consider great friends, and some of whom I'm meeting for the first time and hope will become friends. Yeah, and so maybe we'll start off and just give the panelists a chance to briefly introduce themselves and say a little bit about their work and what angle they're coming at this domain from.
Ziad Obermeyer. Ziad Obermeyer. I'm on faculty at Berkeley. How's this? Great. Yeah, you can have the dead one, Jared. Ziad Obermeyer, on faculty at Berkeley. I'm a recovering emergency physician. I do research full-time now, working with clinical data to help doctors make better decisions and scientists make discoveries faster. One of the major pain points in my work is getting the data that I need to do the work. And so I've also invested some time in building resources for other people to access data, clinical data from health systems, and working with Foundry on some of that. And hopefully we'll talk about that later.
Hope this is not that. Good. Hi everyone, I'm Natalia Vasilieva from Cerebrus. We build very large computers to accelerate training of neural networks and accelerate inference for Gen AI models. I am field CTO, and in my role, I work with the customers, helping them to use our systems to train models for different domain-specific tasks and to also understand how to deploy those models for different applications. So I would say that I'm fortunate to be exposed to many different applications in science.
name's Liam Fettis. Before I was running the post-training team at OpenAI, and tries to make sure that models are useful, not just max out like a math or coding eval. That was until 2 months ago, where then I started a company with my friend Doge, and we're creating AI scientists, starting in physical sciences and material science.
Hey everyone, so I'm Charlie Laurent. Sorry about this. I'm a senior machine learning engineer at NVIDIA, where I work in the physics memo team. It's one of the main efforts of NVIDIA.
Models for scientific applications, and before that I was doing a postdoc in research at Stanford.
Awesome. Thank you everyone for the introduction. So, one of the themes of today is we're trying to discover whether science is a field. I think Ziad funny comment about this with regards to AI for health, and we're trying to understand what are some of the root node problems, what are some of the common themes across the domain of AI for science. Are there certain that are motifs that are of greater importance in AI for science problems generally, or are these all singular domains to some extent? So maybe let's start off there, just talking about root node problems, talking about in deep learning, we're very fortunate. Scaling these things that generalize very well. I want to understand in AI for science, like what are some of the upstream things that you guys are thinking about as kind of enablers? Maybe let's start there. And I think Ziad, you already kind of kicked this off, so I'll give it to you on perhaps.
Yeah, I think it's probably one of the things that differentiates people in this room who kind of work with data in AI directly versus consumers of AI is understanding of data. And I think this was alluded to on the first panel. A lot of progress has come, by having not just compute architectures and things like that, but having nice, well-curated, accessible data sets that people can actually use to do stuff. And I think that is, working in health, I think that's been a huge problem, because in addition to all of the standard problems that come up when you're trying to build a data set, actually getting the data set out of health systems is incredibly difficult. And I think that the reason it's so important is because right now the data sets that we have in health are largely things that are like, okay, here's a bunch of x-rays, and here's what a radiologist has said about that x-ray. And you can recognize like the ImageNet playbook in those data sets, and in this world, radiologists are basically just really highly paid MTurkers. But it's just humans labeling images. And I think that's good if you want to automate radiologists are expensive, we want to automate them, we want cheaper stuff, great. But that's not science. Like science is by definition stuff that we don't already know. And so for that, we need models to learn from patient outcomes, not doctors. And so building up those kinds of data sets where models have the opportunity to learn not from humans, but from ground truth, I think is a really important problem in health and in many other fields.
Very interesting. Yeah, maybe Charlie, can you talk a little bit about world modeling and some of the work that you've done that seems kind of related to this theme, and maybe you can talk about Physics Nemo in that context.
Yeah, sure. So one of our greatest success in Physics Nemo is in weather and climate, and one of the reasons for this is because I would just say data was already readily available. And the reason for this is because there are some organizations like NOAA in the US and ECMWF in Europe that have been working with cloud storage providers for a decade already. So all their data sets are already available and easily accessible through APIs. So it's very easy to use for machine learning developers. And maybe something even more important is that they already invested a lot of efforts into high performance storage system. Because if you have a very big data set, right, but you need 1 week to even download it to your cluster, then the data set is just totally useless. right? So, for example, there is the example of the ZAR format. They invested a lot of effort into developing the ZAR format, and now, like, the field is kind of moving in this direction. And at least in our team, we believe it's like a standard that should be adopted by a lot of users. And now we are trying to go to different domains in physics anymore, like CAE, for instance, aerodynamics, CFD, and this is the bottleneck there, because we are kind of like 1 decade behind in terms of data availability and accessibility and also throughput. So yeah, that's the bottleneck to develop those new AI applications.
Very interesting. Maybe jumping to Liam, you were originally trained in physics, and then you became an AI researcher, a very prominent one, and now you're back to AI for science. Could you speak about that journey and maybe what precipitated that and how you see the kind of problems in AI for science that were worth your dedication?
Yeah, sure. Also, maybe I could answer your initial question too about sort of generalities.
Yeah.
I think as we think about AI for science, I do think that there's a general set of properties that we need these systems to have. The ability to create hypotheses given some data, like explanations, hypotheses, conjectures. Given those, carry out valid experiments. So is this a sensible, is it a well-formed experiment? Does this make, in the context of your hypothesis, as well as being able to analyze your experimental data. And this loop, I think, is very generic. To address it in like that sort of like vague term, I don't think it really makes sense. I think you actually have to like go to a specific field and actually like do the full loop. So I think that's like one common theme that's going to be present in like a lot of these technologies.
Makes sense. The kind of the process of doing science in some ways, the scientific method is a very general,
Exactly.
general extensible.
Exactly. Automate the scientific method.
Yeah, I think I will piggyback on that because we don't talk about, I don't know, statistics for science. We use statistics in science, but there is no field of statistics for science. I view AI as a tool, which, yes, should be used for science, and scientists should understand how to use AI tools to further improve on their research. But I don't think it's a separate field on its own.
Very interesting. Yeah, maybe kind of double-clicking on the problems that you all are working on right now in AI for science. Maybe we can start actually with you, Natalia. You've done some work on molecular dynamics simulation.
Yeah, I think
I'd love to understand that.
That's a perfect example of science, and I've been chatting with Boris before, so I can talk about AI, I can talk about hardware, I can talk about science, I can talk about some examples which bridge those three topics together. So this molecular dynamics that you mentioned bridges science and specialized hardware. There's no AI there yet. Maybe we'll get to that. So example that Jared mentioned is our specialized chip has been used last year to develop a molecular dynamic simulations for metallic alloys, which runs almost 750 times faster that you can run on all of Frontier. That's an exascale machine at Oak Ridge. And when we talk about scientific applications, even beyond AI, some of them are really hard to scale on existing hardware, and specifically for molecular dynamic simulations, if you think about that, molecular dynamic, it's you're simulating atoms, right? Newton force, how atoms behaves within the molecule. You want usually, you can scale in two dimensions. You can scale in size of the system, so you can model billion, trillion atoms together, and that can run very well on existing infrastructure because you scale out. You do some part of atoms on one node, some other part atoms on another node, etc. But that doesn't allow you to scale time steps. In order to simulate those atomic forces, you usually want every time step to be at the resolution of femtosecond. So you need very fine-grained resolution. But at the same time, physics phenomena, they usually emerge at hundreds of microseconds. So in order to simulate hundreds of microseconds in this femtoscale resolution takes a lot of steps. And that's impossible to scale on existing infrastructure. And that's where our machine actually shined. And that one enabled us to be so much faster and increase the scaling of that time steps, which almost got a Gordon Ball Prize award for us. But again, that's an example of classical molecular dynamic simulations, a classical science physics-based approach, which is applied to completely new hardware. There is no AI there yet. I hope that in the future, and we're looking into that, and there are some algorithms how to approximate some of those classical simulations, physics-based simulations with AI, and that's very interesting.
Very interesting. Yeah, I see a couple of common themes starting to emerge. I guess the point that you're making there, Natalia, is the compute, like the types of workloads that pop up in some of these scientific domains. To some extent, they're scale-outable, they're parallelizable, like physics simulation. They can benefit from these technologies built for GPU, for AI workloads like GPUs. But to some extent, they're also bound kind of depth-wise, and you kind of have to scale up as well. And you need speed because of the resolution, kind of being pushed to the extreme. And okay, very, very interesting. I think we're gonna maybe get into part of the different chip architecture approaches on that. Yeah, maybe let's just to ground some of the kind of infrastructure conversation in some of the model and data conversation in what people are doing. Maybe we could talk a little bit about some of the problems people are working on. Liam, I think I'd love to hear kind of about the problem in AI for science that you've kind of been drawn to.
Yeah, thanks. So what we're trying to do is create these scientific systems in material science, in the physical systems. We're beginning in a fairly narrow area. We're thinking about like solid state powder synthesis. That allows us the ability to study things like ceramics, dielectric materials, but one thing we're really interested about is higher temperature superconductivity. It's a continuous reward problem. We'd like to see if we put a lot of optimization pressure against it, how high can we get that? And if we fall short of room temperature superconductivity, we still have to produce systems that can do automatic synthesis of a new material given a crystal structure, automatic characterization, so given you produce some stuff, what is actually in it? Or you can also produce other improvements to superconductors, like improvement to critical magnetic field, ductility, so you can turn them into wires more easily. But I think there's something very foundational here about a system that can understand and manipulate matter. Quantum mechanics is very fundamental, and I think there's this really great opportunity to bring together a few different fields in order to produce very strong systems here. And Doge and I were sort of looking at a lot of the developments that have happened in even just the last couple of years. So improvements to language models, reasoning models, high compute reinforcement learning, synthetic data, improvements in robotics, and then also improvements to in silico material design. So the ability to simulate these systems, produce some scaling laws, and predict and actually synthesize things with very high probabilities. And so I think we kind of took the stance that this is a really great place to begin for AI for science. It's very foundational. Also, there's a huge amount of value to materials. For most advanced industries, you're bottlenecked on the materials you have accessible. And with respect to other fields, it's a fairly fast iteration cycle. So the thing that we're starting with is possibly doable on the timescale of a day. It's unregulated, and you have some simulators. So those sort of the motivation for beginning in this space. And also just kind of getting back to some physics background.
That's awesome. Makes a lot of sense. So maybe as a way to kind of circle back and kind of go through the understanding, the extent to which there are common themes across these areas. I'm hearing a couple already emerge. So maybe we'll double click on some of the models questions. Then we can talk a little bit about some of the kind of compute and infrastructure questions and bottlenecks. I think that would be a really, really interesting way to go through this. So maybe what I'm hearing is that it seems like one of the themes that's popped up a couple times is reasoning is kind of an unlock in AI for science. There's something about the scientific method overall that, maybe that's the right level at which to insert, is to kind of try to build an AI scientist as opposed to treating every problem as a discrete problem. And so reasoning and kind of these models that can apply test-time compute, this breakthrough, is one of the things that's exciting people about this area. I'd love to probe that more, see what people think. It seems like there are some kind of common themes or themes within ML that are more important. Another theme that's come up a couple times is simulation and world modeling. You mentioned synthetic data and even synthetic gradients, these types of themes. And so, what do people think are some of these modeling themes, some of the ML theoretic topics that are of greater relative importance in AI for science context than kind of the general AI world?
I can give one thought on this, based on a project that I'm doing now, where I think AI is playing a couple of distinct roles in the scientific process. So this is a project on sudden cardiac death. It's exactly what it sounds like. People just drop dead with no warning, and doctors are very, very bad today at figuring out who this is going to happen to. The cause is an arrhythmia in the heart, and I think what makes this particularly tragic as a problem is that we have a solution to it. We can implant defibrillators that terminate those arrhythmias, and the problem is we don't know who's going to get the arrhythmia in time to put in the defibrillator. So really, really nice machine learning problem, because what you're trying to do is predict this thing that's going to happen. And so we have a partnership with a regional health system in Sweden where we get all of the electrocardiogram waveforms that were ever done in that region. We link it to death certificates, because in Sweden you can link everything to everything, and we just predict who's going to drop dead in the year after they get their electrocardiogram. And this thing works really well, like much better than what doctors are currently using, which is a metric derived from cardiac ultrasound. And so I think role number one for AI is a role that's very familiar to everyone, which is predicting some empirical thing about the world. There's a pattern in the EKG that's linked to this thing. It found it. Awesome. And that's really useful because it can be used to allocate the scarce resource in a clinical setting. So awesome. But I think, one of the nice things about working with data that come, not from like the electronic medical record where doctors have to write notes, or from billing records, which you're working with an electrocardiogram. That is like it's a biological readout of an electrical field in someone's heart. And we know a lot about where that field comes from. And so here's the second role for AI in this process. We train a generative model of an electrocardiogram waveform. So artifact one is map from waveform to outcome. Artifact two is produce the waveform. But now we can chain these things together, and we can ask the generative model to produce waveforms that are higher risk. So I can take your EKG or my EKG, feed it through the generative model. Now it's in latent space. Now we just follow the risk gradient of the predictive model and turn my EKG, which hopefully is low risk, into a progressively higher and higher risk model. Okay, so step three is currently still a human step, but eventually you can see where this is going. So now I can look at the high risk versus the low risk waveform, and I can use my neural network to say, oh, I actually see the difference here. This squiggle is coming at the terminal part of depolarization, and it weirdly looks like this waveform is kind of scattering on something. And then we can go correlate that to cardiac MRIs, and we find a much higher rate of very subtle but diffuse cardiac fibrosis in the hearts of the high-risk patients, and none in the low-risk patients. But you can see how there's a third sort of computational artifact that eventually, we have computational models of the heart, and those models start from biological and physiological primitives about the heart and can build all the way up to an electrocardiogram waveform. So now we can actually chain these three objects together and go all the way from the empirical fact about the world to the waveform to the physiology of the heart. And I think that kind of loop, that Liam, you alluded to as well, like those things are super exciting because that chain from real world to the lab is super powerful for generating new knowledge.
That's very neat. It sounds like DPO, plus it sounds like kind of using generative simulation models, DPO for a scientist, like these things that were originally used to optimize friendliness in language models can be used to. Well, it was pretty interesting.
And maybe another answer to your question too is, I think one thing that's really foundational for science, and it kind of builds on this recent advance in reasoning, is search. I think this kind of also builds on Zayed's point about how do you, what is science? And it's like, well, you're sort of extending the frontier of knowledge. It's not just producing predictive models. And there was a recent paper from DeepMind, AlphaEvolve, and I think it was very impressive results. And basically what it's doing is leveraging just inference time, test time compute to have these systems, like the reasoning type systems, to produce new evolutions on code, but it's a very generic thing. So I think search is a very foundational thing, and now with these reasoning models, it's going to become far more effective, and you could go beyond just evolving code, but evolving on many different types of things. So like in our context, perhaps you're doing evolution on a synthesis recipe to produce a new thing. So this is like, very recent technology. And also one thing that's nice about this too is by decoupling search from the parameter updates, you're sort of simplifying the problem and really focusing on this thing about like, okay, can you push frontier of knowledge from these systems?
Very nice.
Yeah, I would like to actually bounce back on the example of the EKG. So the physics NEMO team started, or in the early days, we started to work on models that strictly follow physical laws. And when we talk about AI for science, we have to talk about physical laws. And in the EKG example, there is a physical law that links the abnormality in the signal to some abnormality in the structure of the art, like some material properties, something like this. It's probably a very complex problem. You'll need to run some simulations to do it. But nowadays, we started to shift more towards purely data-driven model. So we kind of gave up those physical laws. Like most of our AI weather forecasting does not follow physical laws. It's purely, they have some kind of a physical inductive bias, but they don't strictly follow physical laws. And I know there's a lot of current research on how to blend the two together, like physical laws and data. But for now, there's not like a magic recipe that works across multiple domain, multiple equations, and sometimes we don't even know the equations, right? Like in this case, we don't know an explicit equation between the two. So we haven't found the magic recipe to incorporate physical laws and data in the same model.
Makes sense. So it sounds like a lot of the themes that we've worked on kind of have been pretty elegantly adapted. A lot of the general ML themes to AI for science, it sounds like, and just general better generative models that can learn patterns from data, that can general models that can learn patterns from data. Being able to kind of roll those forward. Kind of preference models that can take kind of optometrist algorithm type things. Seems like these are all common. I'm wondering if there's something different about the data regimes that we're trying to simulate, or the regimes that we're trying to learn over, that maybe necessitates more focus from the community. If I'm an ML researcher in the crowd, I'm wondering what types of problems I should be thinking more about, what types of data regimes. Natalia, you mentioned kind of the frequency of the data, kind of the resolution and the scale is one kind of notion. So we mentioned EKG data. I'm wondering if there's something about the regime, it being continuous data, it being time series. Yeah, wondering what types of things kind of we can draw out here.
Yeah, I think there is definitely something there. And actually, when you start asking that question, I jumped not into molecular dynamics, but into models that we are training on DNA sequences. And I think my team in general, we know how to train language models. We know fitted many scaling laws to many data sets. We know most of the compute efficient ways to train that. But their statistics of the data in language and DNA, just the fact that in DNA you have only vocabulary of 4, and we know that human genome is 90% of us sharing the same, even more than that. So the redundancy, the scaling law is not the same. What would be the optimal model size? What would be the optimal token per parameter for DNA data versus language? It's all open. And if you go to time series, again, if you try to use the same models we use in generative AI, it's a completely different representation. So how do you still potentially use the same fundamental understanding of the model, but fit it to a completely different data representation? These are all open questions.
I can speak a little bit about data as I view it too. Thinking back to, say, like the early days when we were creating ChatGPT, we had a higher dependence on supervised data. So given this input, this is sort of the desired output, and supervising the system towards that. But if you fast forward the 2.5 years, now there's been a huge amount of progress on RL environments. So now the shift has become one of data to constructing environments. And an environment is basically something where you have some sort of question, some input, and you have some ability to grade it. As a concrete example, what is 2 + 2? You know the ground truth is 4. You can put a lot of optimization pressure against that. And I think a lot of the work now becomes, and this is like behind like models like DeepSeek R1, for instance. And I think a lot of the work now becomes, how do you construct robust, high fidelity, hard to hack reinforcement learning environments? I think that's become like a big focus on like, how I'm thinking about data from the more traditional thing of just like, a big basket of data or supervised data or comparison data to these sorts of construction of environments.
Makes a lot of sense. And so this is pretty interesting. So it sounds like there are a few themes that are emerging as modeling themes, pretty particular to this regime. Search. Right? That has a lot of infrastructure implications. Much more embarrassingly parallel. It's very different than kind of classical pre-training. Simulation, many different environments, RL objectives, and kind of environment engineering. This spawning many instances of that. Kind of this multi-scale, these multi-scale aspects. So I think that's an interesting, maybe jumping off point to talk a little bit about, kind of compute strategy, what we kind of want out of our infrastructure, what we want to have chips in the future, to start to think ahead now for the kind of chip designer systems people in the room, and then also for maybe, the people who are thinking about their infrastructure strategy. So maybe even before we get into that, we're having some interesting side conversations about just overall how you guys are structuring your teams and your orgs. I'm just curious about how these things are being structured, what the kind of the rhythm, operating rhythms of the team look like, and then we can kind of tie that to a little bit of your infrastructure approach. But maybe we can actually just briefly start with, broadly how you've been constructing your teams, how you've been pursuing these problems, and trying to work with customers on these problems, and what the team composition looks like, engineers versus ML scientists versus domain experts, how you're thinking about that.
The first panel, I think, had a really nice observation about the importance not just of bringing people together from this. I think that there's a sense in these fields where there's domain expertise that the model for producing research is, it's like the joke model of producing it, where you have a physicist, a computer scientist, and a chemist like walk into a bar and then good things happen. But I think that the point that was made was that you need time for those people to learn how to communicate and learn what the other person is interested in and about their domain. I think that's really important because it seems very inefficient for everybody to need to speak all of the languages, but I think that ends up leading to much better work because the interesting stuff is in the interstitial areas between fields. Like if you think about, what problems do I work on? Part of it is what am I interested in, but part of it is also what are other people not working on? And I think other people are largely not working on things where there are two sets of fixed costs to pay to work on them. And so those are really, I'm definitely not smart enough to outrun anyone in any one race. And so the only thing I know how to do is go find some new race to run. And so that's, and I think there are lots of open spaces in these interstitial areas that require being above the bar in two fields.
I can maybe also answer that. On our side, again, so I believe you can think about professional services where a customer comes to us and say, we need a model which predicts patient response to a particular drug. Or we need a model which approximates atomic forces for a nuclear reaction. Or we need a model which does something completely different. So internally we have ML engineers, ML researchers, applied ML researchers, who mostly know how to train language models, to be honest. But then we work with all of those domain experts in different verticals and with different customers to bridge the gap between our ML expertise and their domain expertise and do something new for a particular field. And that's been very interesting, very rewarding, and yes, challenging because we speak different languages at the beginning and it takes time to understand each other. But after that, the sky is the limit.
From our side, we basically have three different pillars. There's machine learning, experimental, and then like computational theory. So we have sort of representation. Right now, the team is highly technical. Eventually, we will have more business-focused people as well. It's 2 months old. And that is basically like sort of like the broader bucket, and kind of building on Zayad's point, like getting the interfaces between these teams is very important. I noticed that the computer scientists kind of think in terms of APIs. They'll just be like trying to do this kind of translation. You're like, okay, I don't understand what you said. What's the input? What's the output? What's the structure of that? And you can start kind of like formulating these kind of bridges. One thing that we've sort of been thinking about too is almost have some of these like bridge people in the company who have both aspects in their mind. So I think Doge is like, a quintessential one. Like, I think he's like basically an N of one in that regard of like world-class machine learning researcher, but also like world-class in like materials. And having like a few of these people to help with the translation. So yeah, I mean, but I think there is so much value in kind of at these intersections. So rather than, just trying to hill climb on like LMSys, it's defining a completely new race. And I think there's a huge amount of value there.
Yeah, so I'm not going to talk about building a team because I didn't build a team. I'm just part of the team, right? I wish I were a manager, but I'm not. So our team is only composed of domain experts. So people with background in CFD, people with background in medical imaging, people with background in material science and whatnot. And we don't have any like generic programmer or computer scientist. Because when we work with clients, we basically need to work hand in hand with them. So we need to be at the same level as those people. So if we talk to some clients working in oil and gas, we have to be expert in oil and gas. And if we talk to some weather agency, we need to become expert in weather. So yeah, that's the way we proceed.
That's interesting to me because one of the things that I've noticed is, I think in AI, we've seen multiple models of kind of org structure. I think the original Google Brain model was one extreme. It was very federated, very decentralized, very grassroots. It's a term that came up very bottoms up. And I think that was partly because we were in a regime where things didn't quite work. And you wanted to let flowers and flowers bloom, see what would work. And that was actually maybe a good model. The scaling laws paradigm is a bit different. In that case, it was like, okay, clearly we've got a thread we can hill climb on now. We probably need to rally everyone around it and spin up kind of one large single tenant run that will be long running. And so there's kind of mixes of iterative, grassroots, bottoms up, small experiments, individual compute allocation, and kind of one big thing. Yeah, I'm curious how this is looking for some of the problems you guys are working on in AI for Science. Is it, you kind of have the core objective function, we've got the environment set up, like the problem's well framed, and it's one big YOLO run? Or is this kind of more of a federated grassroots endeavor where kind of this PI model and individual investigators model is better? Like, how do you guys think about all of this?
I think you have to combine both. So we have a small team which does this bottom-up exploration and grassroots, and we know it's high risk, potentially high reward. They are allowed to run all different directions. But then we have those pods which work with particular customer, which typically reuse recipes which has been proven by their internal teams to work. And that is much more structured than usually at a larger scale because, okay, customers paying for much more compute.
Yeah, I mean, plus one to that. Like, I think like achieving this balance of bottom up, top down is super central. If you're too top down, you sort of like lose all of the creativity and ingenuity of all these like brilliant people on the team. And if you're too bottom up, you just like, it doesn't really add up to anything consistent. So I think kind of striking that balance is very important. But for each of these sort of bottom up, high risk things, really seeking for some predictability of the system. So try to encourage, okay, well, what is the scaling property on this? And then that allows you to put a lot more resources behind it. That's allowed us to plow tens of billions of dollars into language models because of these scaling laws. And I think AI for Science should follow a similar thing.
And I think what this is highlighting for me is that the thing we call science is made up of so many different things. Like there's an explore component to it for sure, where for a lot of the things that a scientist does every day, and certainly what I do every day, like I have no idea what I'm doing. And if I could figure out how to make it work better, I would love that. But it's just, there are some activities that are fundamentally about exploration and that require a very different skill set from very well-defined problems, you know, like protein folding is now super well-defined now, and we're making a ton of progress on that thing. But it took a long time to get to that definition and to get the data sets that allow us to just grind. And so science has these two components of like, there's the exploration and then there's the exploitation. Makes it sound like more fun. It's like you're pulling the slot, but it's like a grind. and that's a big part of science too.
Very interesting. So what I'm hearing is, right now where we're at in AI for Science, it'll be a very kind of iterative time to some extent. There'll be a lot of different teams running smaller experiments, trying to kind of grok which of these is getting lift, so to speak. Then you scale them up to try to understand the scaling dynamics, and then maybe you'll aggregate them into some sort of YOLO run. And so it sounds like it'll be a bit of a hybrid model, kind of a strike model or something like that.
Hopefully not YOLO.
Hopefully not YOLO. Hopefully a little bit better than YOLO. But.
I feel like YOLO has too much of this like fun connotation. Ideally, it's just like no. Those things, it's just like sloppy science. It's like ideally you have it like mostly figured out.
Makes sense. Makes sense. Very interesting. So sounds like so this is starting to get a little bit into questions of okay, how to translate some of this into compute strategy, infrastructure strategy. I think one of the things that's both exciting and a bit perilous is a lot of the recent advances, it seems like in many domains of AI for science, have been fueled by the same types of advances undergirding AI, kind of compute, larger scale infrastructure, the capabilities of the latest generation of accelerated computing kind of devices. And so, yeah, maybe I'd love to hear how you guys are respectively either working with your customers or in your own orgs thinking about infra and compute and how you're navigating all that.
I'm going to start by caveating that because I know nothing about compute, I'm going to talk about maybe the context of the compute. And so in healthcare, the basic problem isn't like too few GPUs. It's that the capacity to do work and the data that you want to work on are just in fundamentally different places. And so all the healthcare data live inside of hospitals or health systems. They're owned by a department called IT. They don't hire a lot of machine learning people. Machine learning people don't want to go work there. It's not like, so that's not a good fit. It's not a good model for scaling up. And on the outside, you have a lot of people, there's so many Berkeley PhD students that are like, oh, I know how to do this thing. I would really like to apply it to some medical data. Can you help me? And I'm like, yeah, we'll get your fingerprints done, and then your tuberculosis test, and then you'll fill out all these forms, and we'll get the data use agreement amended. And then, 3 years later, they're already working on ad click optimization and not doing the thing that they actually wanted to do. And so that is a huge problem for health research, because only a privileged few can actually touch the data. And so it has nothing to do with the compute itself, but it's this kind of political and legal infrastructure around it. And so the things that I've largely been working on in this area have been trying to figure out ways to get the data out of the healthcare system so that you can put it on good compute and in Foundry. And so the two things I'll just mention briefly. One is a nonprofit effort called Nightingale. It's philanthropically funded initially by Schmidt Futures, where we worked with hospitals to build up interesting medical data sets, de-identify them, and then get them out of the hospital. So at one cancer center, we bought some slide scanners. We got the breast cancer biopsy slides that were literally collecting dust in the basement, digitized them, linked to longitudinal data on metastasis, de-identified it, got it out. That's going to be on Foundry soon, so you can just work on it directly there. The other effort is a for-profit called Dandelion, where we have a consortium of health systems, non-academic big health systems across the country. We de-identify their data, the electronic health record data, but also all the imaging and monitoring and waveforms, and we bring that out into our cloud. Sadly not Foundry, where people can build AI products and then own the products that they build on top of those data as a way to get more clinical products being built.
Yeah, I would just like to add something there. So our philosophy is quite different, I think. Like, we don't want to get the data out of the IT department. We want to, we want to democratize AI, and we want people who are already in the IT department to use GPUs and to be able to train their own AI model or run their own inference. And I think it's something we've been quite successful in. And for example, now to run a full weather forecast of the globe at a kilometer scale, you go back home tonight, you can do it. It's like 10 lines of Python. But probably just a few years back, you need access to a national lab supercomputer, and you need to be expert in weather to do it. I mean, I did it before. I have no idea how to do weather prediction with like traditional code, but I can do it with a neural network. I am not an expert in weather, but I can do it. So it's like almost anyone can do it. And yeah, that's the way we think adoption and democratization of AI.
On the compute side, I view two key technologies. One is search, reinforcement learning, synthetic data, those types of things. The second would just be large-scale pre-training. So it really depends on, and I think both are going to be foundational and continuing to do this. Like, I think the search in RL will give you better sort of like, strategies, tool use, reasoning, things like that, whereas the pre-training gives you just knowledge. And I think our workflows are probably going to look fairly balanced, and on something like search or synthetic data generation, you don't require the same level of like interconnects as you would for the pre-training. So it's still TBD, but I think like if we were talking like a few years ago, you'd think huge amount of interconnected chips. Now I think it's really kind of shifted more towards distributed compute a bit in the workflows that we're seeing.
Super interesting. So you have this kind of nice, much more variegated pipeline where you have the kind of large pre-training flow that kind of captures the original base knowledge that you'll then quickly adapt from. Then you have these RL flows, these kind of post-training loops, which are much more distributed, smaller InfiniBand domains, even just fully distributed nodes, single nodes. Very interesting. So the kind of AI factory of the future looks a little bit different. It's not just one large interconnected facility. It's maybe a bit more dispersed. Natalia.
But I also wonder what model architectures for the future would look like. Because to me, it also requirements to compute depend a lot on how, like, which algorithms we run on the systems. Today, we use transformers. What would be the model of tomorrow? I don't know. Will it require the same amount of compute? Will it require the same memory bandwidth? Will it require the same connectivity? I don't know.
Yeah, maybe one more question for me before we hand actually to the audience for some audience questions. We'll go ahead and solicit a few of those. Another thing I'm kind of hearing is the data dynamics are a bit different here. I guess these AI workloads, oftentimes, we talk about 15 trillion tokens like it's a lot, but it's only like 60 terabytes, which is really, really small in kind of classical HPC contexts. But then you run that through like a massive supercomputer with 16K H100s or something, and it costs $400 million. And so like there's a bit of a gap because GPUs are so memory bandwidth constrained. But it seems like in a lot of these science regimes, like you have big data, you have mammograms, and you have, like these things are a little bit different. Yeah, I'm curious actually how you guys have thought about storage and kind of whether new systems are needed there, whether there are bottlenecks that maybe people aren't even talking about. All the, GPU people, all of the aren't even emphasizing these. I'm hearing some hints at that, but I'd love to pull on that thread more. And Charlie, you made a point somewhere around that earlier about the size of the data.
Yeah. So actually, one interesting point of the transformer is that when you talk to ChatGPT, it starts generating the answer before. I mean, you can overlap compute and communication. So you start seeing the beginning of the answer before the model has generated the entire answer, because it's an autoregressive model. You have tokens by tokens. One big problem in the models using AI is that usually many of them are not transformers. So you need to wait for the entire computation of the model to have completed to start sending data over the network. So there is a very big latency in this. And of course, the volume of data is much larger. So a single query from an LLM will be like a few kilobytes, but a query from the answer of a query from an AI for science model, for example, a weather model would be in gigabytes. So that can be very long. And also another difficulty is that when we want to deploy this model in production, the standard way to do it now is to containerize the trained model, or at least your inference pipeline. And when you do that, actually, you need to pull the data to CPU, and that introduces even more latency. So data communication, so both from GPU to CPU and over the network, is going to be even more bottleneck than actually running the model itself. Yeah.
Makes a lot of sense. Does anyone have anything to add to this notion of kind of data hierarchies, kind of data latency, data strategy?
I think, as I said, it's very algorithm dependent and it's very model dependent. And right now, we all trying to optimize for also existing infrastructure. We are building multi-hierarchy memory systems. So we have caches, we have CPU, DRAM, we have storage, we have memory on other nodes. And we're trying to fit algorithms in order to take advantage of all of those layers. For some problems, you can do that. For some problems, you cannot. So answering also maybe a question about storage requirements, language models, yes, they don't require much data, but what if you run generative models for video, if you run diffusion models, suddenly your inputs and outputs are much, much larger compared to just language, and storage becomes important, and proximity of the storage to the compute also becomes much more important. So I don't think, again, there is the universal answer, what's the best recipe to build the infrastructure. It's very problem dependent. And if anything, I think in the future we will see more heterogeneous approaches to compute. Even the fact that Cerebras emerged or other competitors to NVIDIA emerge I think proves to that theory.
Yeah. I'll just point out one thing, which is that I think we're all thinking about doing science as a sort of big science enterprise where we've got data in a place and lots of compute. And in medicine, there's this older kind of science that that has different requirements, to your point, Jared, that I just point out of interest, which is that a lot of medical breakthroughs have come from a doctor seeing a patient with some new technology. So like when x-rays first came out, there's a ton of new stuff that like how do bones grow? Crazy. But you just see that in one patient with a bunch of x-rays. How does a fetus grow? When we had ultrasound, and I think that kind of science is very valuable in medicine, but also in a lot of other places. And that has very different requirements for data and modeling, because that kind of stuff, you would want to have it on the device and at the point of care. And I think that is a very different flavor from the kinds of things that at least I do today. But the stuff I'm going to do tomorrow, I hope, as a doctor, is going to be much more distributed and at the bedside. And I think that'll be really fertile ground for a new kind of science.
Okay, very interesting. So let's start to queue up some audience questions, but I guess I'll note, it sounds like another takeaway is kind of a bit of maybe one that we didn't expect is, it looks like the future will be very highly variegated around the infrastructure here. Like workloads, still classic pre-training, but then also these search workloads in the mix. That's kind of one lesson, is that will definitely be true. It seems like the storage needs and the kind of size of the data and latency requirements are richer and a bit more dynamic than in the past across these AI for science regimes. So there are these, that's kind of a pretty interesting finding. It sounds like, on the other hand, there are these common themes, like reasoning and search. There are these common themes like multimodality, multi-scale, simulation. That's a kind of a common theme, set of common themes. And then it sounds like on the data efficiency side, some regimes have an abundance of data, almost a gratuitous amount, and some are very data constrained. So maybe that's something that isn't common across kind of AI for science context. That's worth thinking about more. Yeah, let's maybe get some audience questions, see what people are thinking about. Does anyone among the panelists have a thought about that?
I'll just say that in healthcare, I think that is a really, really critical issue because there's no obvious label. So in a lot, I think in weather, there are some very obvious labels that, like where did the hurricane make landfall? There's like a good prediction target, I assume in material science as well. There are these well-defined things. In healthcare, there's no variable called health. There's just a bunch of messy stuff, and the stuff is created by people who have incentives and who make mistakes and who just do a bunch of weird things to the data. And so I think that at least what I've found is that set of problems needs to be basically built up one problem at a time. Like there are researchers who spend their careers cleaning one data set. And of course we can't have that model for science, but it's very difficult to imagine a global solution to curating health data sets that's just gonna work for every single problem. Instead, I think that set of things needs to be done from the ground up, one problem at a time, and it's very time consuming, but unfortunately it's the only way I've seen to make it work.
Yeah, maybe I'll add something quickly. The hypothesis that's kind of forming for me is it sounds like AI for science is going to require a bit of a different kind of storage hierarchy architecture where you might have very large data dumps and the classic principle of bring the compute to the data still applies. That'll be your dump, and maybe you'll need to process there or in some intermediate kind of subsampled place. And then you'll need to get down to some very small core set of that data that you can actually feed through a GPU, because GPUs are, these undergirding models are still so memory bandwidth constrained. So kind of in my mind what's forming is, okay, you need some, very, very, maybe less replicated, really cheap glacial store, some kind of intermediate warm area where you process the data and run your algorithms to, do simulations and data augmentation and encode it, et cetera. And then the COT set for that very, very expensive memory next to the GPU. For 1/1,000,000th of your data set. And so maybe that type of architecture needs to be architected really cleanly, and that pipeline needs to be made simple. That's the image that's forming in my head, partly based on these conversations.
Yeah, I totally agree with this actually. Like, we do have some clients who, for example, they want to do their initial data curation on high-end GPUs. You don't need it. Just keep those for training, right?
Yeah, pretty interesting. The data strategy, where to use GPUs versus CPUs. There's a lot of that processing still on CPU, which is interesting, right? And so, very, very cool. Well, let's go ahead and maybe take one more audience question, and then we'll go ahead and stop there.
Yeah, great question. My mental model of the systems is that they're very good where we have a well-defined reward model. So if you have sort of like a programmatic reward model for math, like the what is 2 + 2 example, you can make the model very good at that. In regimes where there does not exist a good reward model, such as like, is this a good hypothesis or not? You can come up with like critiques of that, but it's much harder to grade than like, did you get the answer or 4? So in terms of bottlenecks for search, I think like creativity, conjecture, I think all these things are going to be like very fundamental problems, and a reward signal on that is still like an open question. And then a reward signal on that is to some extent driving like your search process. So it really comes down to like how good is your evaluation, how good is your reward model, and I view these as like multi-year problems. Whereas like if you're searching against did you win the game of Go, it's you can do a very good job there.
Awesome. Well, I think with that, for the sake of time, we'll go ahead and conclude this panel. Thanks again to our panelists.
Asian is Universal API Heritage Month playlist to celebrate the ongoing contributions of the Asian and Pacific Islander diaspora across the globe. Show your support by streaming your favorite API artists like Lynn Lapid, Conan Gray, Toa Bird, and many more. Listen now on
Inclusion is Universal API Heritage Month playlist to celebrate the ongoing contribution.
check. Check.
Ravi Raj has been a partner at Lightspeed Venture Partners since 2017. And there he focuses on artificial intelligence, deep tech, and enterprise software. Before coming to Lightspeed Venture Partners, Ravi Raj earned an MBA from Harvard Business School and a Bachelor's of Technology from IIT Bombay. So as a former product manager at LinkedIn, he says the real key to building successful startups is product centricity. Do you still stand by that, Ravi Raj?
Sure, 100%.
Excellent. But okay, interestingly, or slightly unusually, which I really liked, his bio indicates that he's never stopped learning and that he loves to continue learning. I think that's a great mindset to have, especially if you're going to be at an AI for Science event, of course. And so I suspect all of us will benefit from some of the things that he's learned over the years as he helps us sort of think through this space. So thank you for being here, Ravi Rajan. The floor is yours.
Thanks so much, Boris. Thank you so much. It's amazing to be here. And you know, I would hate to break what just Boris said, but you're not here to learn from me. You're here to learn from three amazing people. We have Pat, Joanne, and Nan. They have insanely cool backgrounds. They're working on some really, really interesting stuff. So I will let them share a little bit more about themselves, their organizations, and then we'll dive into funding for science. So let's start with Pat. Maybe you can talk a little bit about yourself and your organization.
Sure. Yeah, thank you. So my name is Patrick Shafto. I'm a professor of math and computer science at Rutgers, but I'm here today as program manager at DARPA. For those that don't know, DARPA is meant to be the cutting-edge research arm of the Department of Defense, but our purview is actually much broader. So to give you a sense of DARPA's origin, it came about after the launch of Sputnik. And so what they really emphasize is maintaining and avoiding negative technical surprises. Right? So it's not strictly speaking military or defense spending, but things that could be national security risks in a very, very broad sense. And so, you know, among the things that DARPA has supported over the years include unfortunately not better batteries, but instead things like Siri was a spin out from a DARPA program, autonomous vehicles, for example, a lot of early work on statistical AI, which of course became language models and so on over the years. So DARPA's interested in very, very basic things, as well as things that are more defense oriented.
Okay.
So my name is Joanne Pang. I'm a research director at the Amaranth Foundation, which is a part philanthropy, part investment fund. And so we started off mostly working actually in biotech and therapeutics, funding a lot of researchers, helping them spin out and then moving into companies as well. A lot of early stage seed stage companies as well. And then recently we've been much more interested over the last 2.5 years in kind of accelerating neurotechnology and neuroscience research and how that could be, how that could leverage AI advances. And we actually do a lot of like full stack philanthropy, what I like to call full stack philanthropy, which is like funding from hardware, data collection, theory, experimentation, and then also like closing that loop. So that's kind of what we focus on. A lot of philanthropy, about 30%, 40% philanthropy, and 60% investment.
Great. Hi, everyone. My name is Nan Lee. I am a founder and partner of a life science and technology investment firm called Dimension. Our entire sort of mandate is to invest and explore this intersection between the cutting edge field of computer science and sort of West Coast technologies, merging and fusing with the traditional sciences. How that translates is we invest in a bunch of platform biotechs that discover novel medicines, diagnostics, materials, industrial products, using technology as the core lever. And then we also invest in enabling technologies for the field. It could be lab automation or informatics software or things that folks in this room already use from the open source community. We invest across all stages between early company formation, lab spin out, through early stage growth and into public markets. So we see a pretty broad set of the kind of capital stack from company formation all the way to scaled company. We started the firm a few years ago. We manage a little under $1 billion right now across 2 core funds. And we're very lucky to be investors with a few companies that are represented in this room already, and hopefully more.
Feels like we have an amazing panel with sources of funding across government, philanthropy, and venture. Maybe Nan, I'll start with you. You've also experienced like software investing. You've been involved with investing in software companies earlier in your career, and then you're now exclusively focused more on science. Tell us more about how that's different. Like how do you think about software investments as an early stage investor versus investments in science? And are there certain things that you look for more versus less?
Yeah, I think there are many differences. The kind of 2 categories I would call to attention that we think about a lot is sciences tend to be more intersectional and idiosyncratic. The difference between one company and another is greater than in software, where there's more of a playbook that one can learn from training grounds like LinkedIn and then can apply to the next software category. One of the kind of foundational points for us is we felt that a lot of investors only know science really well or only know technology really well and are sort of absent from the other side. And we really wanted to build this intersectional firm where half our team have PhDs and come from labs, half our team have computer science and mathematics backgrounds. We go to ICML and NeurIPS. We also go to ASCO and ADA. So I think that really informs the way we think about companies. And then the other kind of quick point is science moves at a longer time frame. So the kind of waypoints along that journey of how do you know that you're doing well, that you're executing against your vision. In software, you can see the product, it's tangible in month 1, especially now with vibe coding. Customers often come in within the first year of a company being formed, if not the first quarter. So we also think a lot about how do we take those points and apply it to the sciences. And that also tends to be not so templated of how do you measure progress and how do we kind of get excited or not get excited. So it takes a lot more activation energy to do that.
Yeah, I think that's an interesting point, right? Like when you as a founder is looking for an investor, it's important to understand that investor has invested in like science-based companies before, because they have to have a certain degree of patience and nuanced understanding of what milestones really matter. I'll jump to Joanne after this. Like, I first heard about Amaranth Foundation like because of this panel, and I was really, really fascinated. How do you make a decision between whether it's a philanthropic investment versus like an equity investment? And are there any specific areas where philanthropy makes more sense, different stages of the company or sectors?
Yeah, that's a great question. I mean, first of all, I think we all know that the NIH, NSF funding cuts have been made philanthropy a lot more important, especially right now in this current time period. And so I think the way that in which we do philanthropy has also changed in response to that. And like I think like neuroscience is actually like one of those fields where it's like really, really important, where there has been a lot of funding cuts in neuroscience. And it's also one of the places where, you know, there's also a lot of excitement around kind of this idea of like, can we build models of the brain, and at what abstraction levels can we do that, right? Is that at the connectomic level where we have, you know, kind of like a structure or like parts of the structure of an entire brain? Is that at the like electrophysiology level where we're recording, you know, a lot of live data, and then we actually have the hardware tools to scale that data collection? The Enigma project is one of our philanthropic investments, and I encourage you guys to all check them out at the poster session. Or is that like kind of like more cognitive science, like behavioral kind of models? And like that's a lot of, you know, language models today as well, right? It's like capturing the behavioral outputs of humans. So I think like there's actually a lot of really, really interesting, important work to be done there, and a lot of that is not like yet to be proven, right? Like people still have to collect the data sets that make that work, I guess, like applicable and useful for someone like Dimension or other investment firms to come in and say like, now that we've proven this like first model, we can actually, you know, leverage that or capitalize on it. And I think there's a lot of that like basic fundamental science and data collection, and even a question around hardware, like what kind of hardware can we use? Is it electrophysiology? Is it fMRI? Is it in humans? Is it in monkeys? That are still kind of like yet to be explored. And that's like a really good place for philanthropy to come in and fund a lot of those efforts. And I think also like philanthropy is, you know, you can fund really small projects from folks who are, you know, asking, and there's actually like a couple of VCs who have done this as well, set aside like, you know, some amount of grant funding for scientists whose funding has fallen through because of the recent cuts, which is like really wonderful. And then there's also the things that are like larger scale projects, right, that require, like Nan was saying, like interdisciplinary work where you have to have the people who develop the hardware develop that with a specific specification in mind to collect a certain amount of data that has to also go to the people who are modeling that data, and the people who have to like come up with insights and theory and then use that to inform the experimentation. So actually like closing the theory experiment loop is really important and requires a lot of interdisciplinary work, and some of those structures are like really, really good for philanthropy to be able to you know, push forward, because those are the kinds of projects that might not necessarily be done by default in the kind of like academic setting. And we're seeing a lot more universities actually, you know, like respond really well to that. And yeah, so I think there's like a lot of kind of like white space for people to do a lot in philanthropy with.
Maybe there's a quick follow-up question on that. So like, as it relates to philanthropy, do you have a point of view around these are the specific spaces that you want to fund? Is it mostly target areas that you know of or have a point of view on? Or is it that you're basically meeting with interesting initiatives and then making a decision whether that falls into, how much of that is like top-down versus bottoms-up?
I think it's field-focused and people-focused. So like, is the field ready for an initiative that is like a $30 million grant to like push this forward is the first thing. And the second thing, like, are the people there that can make that happen? Because it's going to be likely, for the most part, like at least part academic, even if it is like more oriented like a startup. And so, yeah, it's both of those things. And we get a lot of proposals, and thankfully, you know, on our board, we also have, they're not here today, but Convergent Research is also fantastic in having kind of like capitalized on this idea of like things that are a little too organizationally heavy to do in standard academic labs, but are also too early to be able to do as a startup. And so they actually came up with a lot of the playbook that we use today, and I think a lot of people in philanthropy, especially the people who are doing AI for science, you know, could potentially take a look at as well in terms of like making these teams. But they're usually like, you know, a coordination between like academics and also people who are you know, maybe the engineers that also need to be involved.
Helpful, thank you. Pat, you know, DARPA has always been a fascinating place. You've brought up so many interesting technologies around to the world, right? You know, I took a Waymo to this office, and it was all, you know, driven by initially from a DARPA project. I've heard that there's a very fascinating program called XMath, you know, that's focusing on developing an AI co-author for mathematics papers. That's really, really interesting. Curious to understand what that is and how exactly, what is your view or vision on where this is going?
Yeah, so XMath is a new program. We had an abstract due date yesterday, so we'll be getting full proposals in the next month or two. So the goal of the program is to create an AI co-author for mathematics. I think there's a transformation coming in pure mathematics, and I think it's a harbinger of broader things that will happen to the rest of the sciences as well, in which mathematics is moving very, very fast to formalization, so formal languages, including language like called Lean. There are others as well, because these allow you to prove algorithmically that statements are true, and that provides a great signal for training AI. But of course, the limitation there is that you're working in code, you're not working in natural language math, which is what mathematicians do. And so the research problem is, how do you bridge that gap called auto-formalization and inform? Weird, okay, there we go. Informalization. And then there are other problems that sort of live above that, but sort of that, you can think of that as sort of the inner loop of how do we create this transformation in math from a field that's practiced on pencil and paper to a thing that is formally verified in code and therefore trustworthy.
What does it lead to? So what's your prediction for the next year, next 3 years on where we'll get? Will we be able to solve some of the most complex mathematical problems with AI? How far are we from that?
Well, I think this is a great question. Probably many in the room know that the folks at DeepMind are sort of leading the charge here. So their alpha geometry team had a very nice paper, I think it was in Science or Nature, on success on IMO problems, which are very hard, but still high school level problems. More recently, they joined up with the alpha proof team to achieve even better scores, although there's no paper for that yet. They also have a team working on PDEs. And so what they're working toward is bridging at least 3 different areas of math that have very high profile problems associated with them. So PDEs, for example, Navier-Stokes is a clay mathematics problem worth $1 million if you solve it. So there's that side of things that's happening. I don't know that we'll get there to those grand challenges. It's a very hard thing to predict, but I think, given where alpha geometry and alpha proof are, which is not yet at professional level mathematics, and the PDE team has no results yet that I'm aware of, there's a wide gap between where state-of-the-art mathematics happens and where we are right now, even within DeepMind. And there's another gap that's important, which is between teams like DeepMind, which aren't really pure mathematicians, and the actual mathematics community. And I think those 2 things are really important to overcome before we can get to that point.
What's the biggest barrier for so like advancement of AI in math? Is there something else that's coming in the way?
I think there are 3 main barriers. One is auto-formalization, so being able to translate back and forth between natural language and formal languages, and the bottleneck is data. We don't have enough formalized math. So that's one very concrete barrier. A second barrier is hinted at by the examples, which is the lack of effective evaluation suites. So they're using these IMO problems because they have solutions to them. But in fact, what we want is professional mathematics, which doesn't come with solutions necessarily, right? And so how do we get there from here? We don't have adequate evaluation with respect to professional pure mathematics. And then I think the third is that there's, this all points to an interesting gap in the practice of mathematics, which is that, if you look at a paper, it has structure, right? You can read it from top to bottom. It has things like, theorem, a corollary, lemmas, propositions. It turns out you can reorganize that into a directed graph, right? Definitions at the top, the theorem you want to prove at the bottom, arrows, indicating implications. But what that highlights is that we've got a lot of structure that's implicit in the way we practice mathematics. That's not being made explicit and therefore can't be trained on easily. And so when you look at those arrows, those have all a common meaning to a degree, but they also have more structure that's not encoded even in those. And so there's a whole layer that could be built on top of existing papers and raises the question of like, how should we be thinking about the organization and practice of mathematics going forward? Maybe even papers isn't the right thing to do, but we should be building more systematically, like a software project of sorts.
Maybe one last question in this chain of thought is, if papers are not the right way, is mathematics fundamentally going to change because of this? Are people going to learn math the way they used to, as basically these AI models are able to do and reason a lot more cohesively than humans can?
No, I mean, I think mathematics is going to change, and it's going to change dramatically. I would expect to see within the next year many programs in mathematics adopting formalization into their curricula. You know, eventually the hope is that mathematicians don't have to spend a lot of time programming, right? That's the whole idea of auto-formalization and informalization, but like knowing a little bit about these tools is going to be necessary. And once that transition can happen, you can have tools that can potentially translate a lemma for you, prove it, bring it back to natural language. That has the potential to radically accelerate progress in mathematics. And I think one of the interesting possibilities here is that it might allow us to entertain things that aren't yet mathematics. So the parts of the sciences that can't be pure mathematics right now, right? We can do, physics can become mathematics, theoretical computer science can be mathematics, other mathematics can be mathematics. But things like biology or psychology or other fields like this, they're fundamentally outside the bounds right now. And I think that could change, and I think that would be enormously important in light of the variety of trust issues and associated with data analysis and theory building.
Fascinating. It always, you know, like every single day when you go back and I invest in AI a lot, I feel like what are the things that we should be learning and how that'll be very different by the time my kids are really in college. And I think even like basic things like math and how we learn and how we actually build expertise is going to fundamentally change.
Ravi Raj has a 2-month-old. He's already thinking about his college.
Let's go back to Nan. Right, one of the things you talked about is the milestones you look for in startups are different compared to software. What are the business models really in AI and science that are like maybe examples of business models with companies that are sort of like being turned into effect and are being pursued by these companies? And then second is, as they are making progress, what is an interesting way for the founders to actually express that progress in a way that can attract a larger set of investors than only a handful? So two questions.
Yeah. I think as everyone knows in this room, sciences have historically been mostly around products. So I use the term loosely, but you know, sciences are about advancing some type of product that has utility in the world. It could be a special material. It could be a medicine that has some sort of clinical effect. It could be some sort of superconductor. So the tried and true business model of science is to invent products that have use in the world and then commercialize those products. You know, I have a drug. There's a market for how to make drugs, how to take them to clinical proof points, and then how to generate outcomes. So that tends to dominate, you know, even in this kind of new field, emerging field, AI for science. What we tend to see is that many companies are using computational techniques, AI, to drive faster product building, but really following in the footprint of the scientific kind of biotech business models. It's still, you know, very product oriented. I think as the technology has overcome, and I do think we're there now, has overcome the core initial threshold of skepticism by the industry, in that if you talk to a normal, sort of an everyday representation of, you know, industrial products or pharmaceuticals, they are now honed in that this technology is a game changer. You know, this was not true 10 years ago, maybe arguably even 5 years ago. The average pharma exec could not care less about AI. That's like not a thing that they, you know, thinks deserve merit in their industry. So as that kind of threshold of understanding and respect moves, it opens up new business models. And you're seeing that literally right now. So the two other business models that have emerged are partnerships, value share partnerships, which is a way for a large company to team up with a smaller company. And the undertone to that is there's an awareness that the capabilities of the startup can't be homegrown. And that's why the larger companies are participating. So the recent isomorphic deals with pharma, Novartis and Lilly are good examples of that, where they're essentially collaborating on making products, but rather than waiting for the products, the large companies are coming in and saying, we want to be first in line. You know, Novartis gave Isomorphic $50 million just for the attempt to build a new drug. And that, you know, within 1 year of that company's existence, that's a tremendous amount of revenue coming in that helps to offset the build costs. So that's an exciting new model, which is value share partnerships and co-builds. And then the third business model is in the world of software. So as these capabilities built out by, you know, really interesting pools of data with, you know, ML annotation on top, you know, these capabilities, if they can be generalized, then they can be licensed. So we're starting to see the emergence of, you know, data as a service, model as a service type of businesses where there's not as much shared upside, but there's also not as much, you know, project-specific work to be built out. And there are some companies, maybe one that's more well-known here would be Cradle Bio, which is a London-based company. You know, they're an ML company, but they don't partner and they don't build products. They just license software. And they're getting pretty interesting adoption from the top industrial, pharmaceutical, healthcare companies, you know, to access that technology. So I think we're entering a better world where for everyone in the audience, there are now different modes of how you build your businesses, how you turn your technologies into businesses. You don't have to follow one path. And my expectation is that going forward, we're gonna see all three of these general constructs thrive. And it's not gonna be, you know, a one size fits all approach to how you build a business.
Maybe to double click on one of those things you said, value-based partnership. There could be a struggle in the founder's mind around when do you start having those conversations with these large companies? When is too soon? When is too late? And do you have any guidance on that? And how do you navigate that, you know, that quest?
Yeah, I think as a new company or when you're really small, it always feels good to get the attention of some large respected company in the industry. It could be Google or DeepMind or Pfizer, if anyone respects pharma companies anymore. You know, there's always like the allure of let's do something. And that's a very good point, which is not all partnerships are created equal. There are ones that could be even, you know, from a P&L perspective, negative in that the work that it takes to service that partnership is more than you're getting. So I think it's less about timeline. Like I think that there are isomorphic companies that have great partnerships early. There are some companies that take some time to get the right ones, but it's more about the right kind. And the right kind of partnership to me is value accretive for the smaller company. It doesn't take you off your plan, so it has to be sort of in line with the tech roadmap, the kind of scientific roadmap, and it doesn't, you know, take you away from what you want to do if you had your own agency. And then it has to have value share on the upside because you don't want to do a bunch of work to build some great outcome on someone else's behalf and not take, you know, a portion of that. So that's what we try to coach our companies to not just go for the shiny announcement and they want the headline, but that under the hood, they're really thinking about, hey, these partnerships are super interesting. They help us accelerate. This is not the best fundraising environment. It's you know, really great to get cash in. So they just have to be, you know, very selective.
Maybe I'll go to Joanne. One of the things I was told that, you know, Amaranth Foundation is actually spending a lot of time in neuro research. Curious to understand if you can talk about like Enigma project or anything else around neuro research that you all have been spending time and funding, and some of the reasons why you think that's important.
Yeah, so when we first launched as a foundation, we were funding mostly bio research, actually, and we were we had come up with like a broad list of categories of things and projects that we wanted to fund. We actually went in and we surveyed a bunch of academics. We were like, what are actually the bottlenecks to what you're doing, and can we collect that data set, or can we fund that project, or like, if it's talent, can we actually, build a summer program that, gets more people excited and interested in this field. And we funded a lot of kind of one-off or renewed over a couple years kind of projects. And that was actually very difficult because our goal was to kind of fill in the gap between something that could be NIH fundable and then would eventually become NIH fundable, but might be a little bit too moonshot, or maybe the professor that was involved was in a different field and wanted to switch fields, and then they were not fundable by the NIH. And so we did a couple of those things. And they would come back in 3 years and then be like, okay, great, either we need more money, or this is still something that the NIH doesn't respect or doesn't fund, or it's not something they're willing to put a lot of time and effort into doing, despite us and the general, I guess, audience thinking that it was very useful. And when we moved into neuro, we kind of decided to change our strategy a little bit. We started with a question, which is where do we want to see the field becoming in the next 5 to 10 years? And for us, that was we want to create models of the brain. We want neuroscience, we want to unlock even the possibility of being able to do virtual neuroscience. So neuroscience experiments are very, experiment intensive. Maybe it takes you 6 months or 2 years to train your monkey or your mouse to do the very particular thing you want. Bio PhDs are 5 years, neuroscience PhDs are 8 years. There's a reason for that difference, right? And that was kind of the goal that we wanted to get to. And then we started there and we said, okay, who are all the people that we can talk to? We talked to 300 neuroscientists over the span of 6 months, just trying to figure out what is the lay of the land, what are people doing? And we had this consistent response that was we are not building models of the brain, we're trying to understand it. And it's well, what are you doing to understand the brain? And it was well, we're collecting all this data and then we're building models, but it's not of the brain, it's of this particular hypothesis or experiment that we have. And we wanted to move kind of see whether we could move the dial on that towards kind of maybe less hypothesis driven, more data collection. Could we actually leverage all the tools that AI progress was showing, and what is kind of the minimal project that would be able to kind of even prove that we could build models of the brain? Was there some lower hanging fruit that we could use to do that? And we actually spanned all the model organisms. So we talked to all the C. elegans folks and the Drosophila folks, the fish folks, for those of you guys who don't know Drosophila, the fly people, the mouse people, the monkey people, the human people, and then we spanned actually all of the potential recording technologies and data collection technologies, so optical microscopy, and just went through all of that and then kind of asked the question coming back from that as an external viewer, which I think was very important, because once you're in a field, you're kind of dedicated to knowing, what the possibilities of are. Like many startup founders, you kind of convince yourself that this is the most important thing, and it is. We do need people to make progress individually on each of these fields, but as a field, what was kind of missing was, the monkey electrophysiology, very, very high quality data. At least that was kind of the place that we saw, needed a lot more data collection. And so that ended up becoming the Enigma project, was to kind of build the first foundation model of the visual cortex. And this is very important in order to be able to control the inputs coming into the system, and also being able to scale the data collection with the currently existing hardware, not in addition to funding the hardware that would take 5 to 10 years to develop, or the data collection technologies. To start with what was currently existing, what was the gold standard, and asking the question of, is anything scalable here? And I think we were very lucky in terms of the time and the place and the people, that the field was very ready for that.
That's really fascinating. And what are some of the end goals of that? If you have to predict 3 years down the line or 5 years down the line for that research, what could be if you have to paint a future where this research has progressed, we've made breakthroughs, how does that change the world?
Yeah, I mean, if you want to know more about this, you should talk to the Enigma folks. But I think for us as a funder, they're collecting like a data set that is like 10x larger than all the current electrophysiology single neuron, single spike data that has currently been collected in the last 100 years. And so that's just like to tell you like the level of scale that is possible and could only be possible right now. And so I think like that in itself will be like a massive resource for like people, not just including the project itself, but like other people to go and take a look at that data and, you know, ask the neuroscience questions that they want to ask. That's one thing. The second thing is, I think like the idea of like, can you build a model of like a neural process in some sense? In this case, it's like visual perception. Like, is that even possible? What do you get from that? We've never had enough data to be able to ask the question of like, you know, if I put all of this data into a transformer, like what would I get out of it? Would I be able to predict neural response? Would I be able to predict, you know, the videos that are being, I guess, like played to the monkey while we're collecting this neural data? I think like a lot of those questions, we've just never had enough data to be able to really understand. And then the last thing that would be really exciting is like, you know, could you perform experiments virtually on the model instead of on the monkey, and then be able to validate it, to actually close the loop of theory and experimentation. And I think many people have tried, and it's one of the things that is really hard most of the time with neuroscience is that like sometimes you have to kill the animal or sacrifice the animal in order to be able to get like maybe something like a connectome, something more static. And the question becomes like, how do you validate your data, right? But like here, like, you know, everything is alive and continues to be alive, and you can go back to your resource that you're studying and collect that data again.
One of the things I'm realizing after this conversation is, you know, data is the key, right? When it relates to math, as it relates to neurosciences or any other space. And makes me feel that, you know, LLMs had it easy, right? Like all that data was sitting in the internet waiting to be, you know, tokenized and trained on, versus here you have to build the right data sets, you have to build the right evals to get forward and make progress. But that's really the most exciting part. I'll just like start throwing questions to all three of you, and you can pick. What are the most exciting spaces where AI, or segments of science where you think AI will drive the most acceleration in the near term?
I think that math is a great candidate. I think it's a great candidate precisely because there is a signal. This came up earlier in the morning, right? When you get down to formalized math, at least, right, you have a signal that says this is true or this is not. And that means you can generate data to train on. There are, as I said, huge challenges to getting there because most math is not formalized. But there's incredible incentive to do so. In particular, right, reviewing is a huge burden, especially in mathematics. Takes years sometimes to review papers. And so, you know, getting to this place where we could actually just check whether something is correct in a fairly automatic way would be a huge step forward. So the community, I think, has a lot of enthusiasm for it, just on a very basic practical level. I think the other aspect that I think is really potentially interesting about mathematics is, and I already mentioned this, is about trust, right? Trust. Mathematics is a good environment to study trust and the role that formalization is going to play. And so I think it could be a model system, so to speak, or already is in some ways, for other sciences and where they need to go. Mathematics had crises of trust in the past. They changed this by changing their culture. So you don't borrow other people's technologies without proving them yourself. That's culturally unacceptable. And that's important, right? You have to recheck things over and over again. They also have a very, very standardized way of educating students, right? And that ensures that there's enough common language that you can do these kinds of things. Obviously, if you get to subfields, it can be very, very difficult to talk to each other because the technology that's built in mathematics is so complex. So I think that, you know, there's you know, technological reasons, this ability to have this signal, but there's also sort of important reasons why we should care and drive this forward.
It feels like math, you know, if AI can do math and actually invent new math, you could see that as the plausible part to AGI, really, right? Because math is the way you describe or understand the world around you, right? And if you have that tool, if you can keep massively improving on that, you would be able to, in some sense, discover new laws of physics. I don't know.
Perhaps, I mean, I think this is a great question, right? Like, this is actually an age-old debate in mathematics. So famously, Hilbert said about geometry that he wanted to reduce point, line, and plane to be able to talk about table, chair, and beer stein, right? So he actually wanted to remove the meaning of it and create a syntactic system. And this is often the way people think about mathematics. This is in stark contrast to other folks who came along later, like Wittgenstein, who talked about the foundations of mathematics as being very, very different in this way. And I think, you know, where we sit now is sort of an in-between, where there's, you know, a heavy emphasis on proof and unification and syntax, but also an acceptance that, you know, there are certain elements that we don't need to formalize all the way, and that's part of the challenge with creating actually fully formalized mathematics, is that in papers, informal mathematics, not all the details are written. And so I think there is this interesting tension in mathematics, and I think it's a tension that's related to this question that you're raising about, like, how do we talk about the world, and how do we think about the world in formal languages and also make progress? And so I think there's a sense in which we can really change how we do so going forward.
And I think per Joanne and the Enigma project, and a lot of the posters that are here today, the intersection of AI and biology is extremely interesting. I think the two fields are a natural fit in that biological systems are extremely complex, hard to describe or annotate, you know, from a formulaic basis or deterministic basis, but they're not non-deterministic. They just have very complex relationships, and it seems like large-scale ML models and a combination of pre-training and post-training can pull out these relationships and create these causal predictions that are getting quite good. So I'm very excited that that represents, you know, breakthroughs and soon to be announced breakthroughs in the next few years that drive understanding of chemistry, molecular dynamics, protein-protein simulation, and those are the crux of the issues that prevent drugs from getting to market or prevent materials from being discovered. And I think I see it now, like component by component, those inputs to these big commercial outcomes are being increasingly addressed by really great research from the field.
Maybe we talk about things a little bit more, you know, longer term, right? Like 10 years, we are all sitting here again. What do you think, what's your prediction for how science evolves? Would we, as a result of AI? And I think it's sort of like some of the things we talked about feeds into it, but I'm just thinking, like, really going forward when we probably have 100 times more compute in this world, the models are a lot more powerful, we've probably collected all the data and built the evals. What is your favorite prediction for the world as it relates to AI and science for 2035? Anyone can start, whoever.
I mean, I'm happy to start. I don't know. I think I've been really fascinated by the idea of being able to, like, see systems in real time. I think, like, that's one of the, like, most beautiful things about biology that sometimes I don't get from models, is like being able to see, for example, if someone, I think in panel 1, said, you know, the virtual cell, for example. It's like, I want to sit inside a virtual cell. I want to observe the proteins and the things that are happening in real time, even if I can't see it, right? It's a complete blob. Maybe I slow it down to, like, 10 to the, I don't know, 10 to the 12 times slower, right? Because picosecond scale. I want to be able to, like, observe a system. I think that's one of the, like, most beautiful things that you can really get. I think I was fascinated with space launches because I was like, you can actually see a thing that we have built, and you can see it being launched into space, and you can, like, look at it and observe it. And that's the thing that I've been wanting for most of my life around biology and neuroscience, is to be able to see those systems in real time do the incredible things that we know that they do, like evolve and, like, compete, or, like, cognition, or, you know, all of the things like respond to drugs or like grow and evolve as a system. And I think like that would be really, really incredible if we can have these models, these predictive models also tied to an ability to actually like visualize the system and like show people how incredible the world around us internally is just as much as the world that we can engineer and build.
Building on what Joanne said, I think one key piece to doing that is having the ability to automate abstraction, right? Which pieces of the data are you going to represent and how, in order to make the visualizations or the expression of the data tractable. And I think that's one of the sort of central points about mathematics that we introduce, is that we abstract things. Alfred North Whitehead has a really fantastic quote that goes something like, when you take away all of the extraneous pieces and get to the universal properties, then you have the abstractions that you need in order to do mathematics. And so I think there's sort of a sense in which, and again, building on Raj's earlier point about connecting to reality, that in the not too far future, we could have a flexible method for doing that kind of abstraction, where you might get a visualization of one kind and be like, well, I'd rather something slightly different, and then like you could actually transform that potentially. And I think that would be fantastic.
Any?
I just think we'll just have a much better understanding of the natural sciences, ranging from the molecular behavior of compounds and chemistry to biological systems and disease expression, disease rescue. How that realizes just big, bold claims is order of magnitude more drugs will be discovered in the next 10 years than in the last 10 years. Drugs will be targeted to smaller audiences that have more defined disease states because of all this great data that we're understanding. And I think you kind of see it if you look at the field of cancer today than 20 years ago. Like, no one has lung cancer or breast cancer or how these things used to be annotated. They're now like extremely genetically defined. They're surface biomarker defined, and our treatments are similarly precise. I think that whole thing is going to happen in every disease area, from neuro to inflammation to all the things that plague us. So I'm very optimistic, and I think it's driven by large-scale data generation capabilities, and then all the great technological advancements in ML.
Related to that, I think my fascination or my fantasy about the next 10 years is that we'll have a model for every human being, which is basically a biological or neurological model of your entire existence. And you can, and you could be the data source for that model, and you could be the eval for that model, so much so that we have a perfect understanding of human body, human emotions, in a way that allows all of us to maximize happiness in our goals. I'll stop there. I know we have a few minutes, and with such amazing people, I want to make sure if people have any questions, we answer those. But otherwise, it was an absolute pleasure getting your perspective and hearing about all the fascinating things you guys are all involved in. Any questions here?
To be successful, Tesla being a perfect example of that. How do you foresee AI-first companies, or rather companies that start from an AI, from an idea that comes from, say, better modeling or better execution through the usage of AI technology, attempting to verticalize, right? So before you've mentioned that one pattern is effectively working with other companies. Larger companies already have the stack to be able to use better modeling, but often that's not possible, especially in things like energy or more traditional industries. Do you think there is a path there where an AI-first company or an AI or a company that is primarily about AI could move into doing everything through, say, VC funding?
Yeah, I mean, my answer to that would be, that is the default path. I think you have to assume you must verticalize unless the market tells you otherwise. And then actually many companies make the mistake of not doing market discovery, thinking that they can sell software, sell capabilities. Partnerships is just a different way of doing that. And if the industry isn't sort of set up well to be able to connect with you in that way, guess what? You're now an energy company. and I think we see that time and time again.
One more question if there's.
Hi, thank you so much for the panel. One thing you said was that we're living in a world where AI can create mathematics that humans haven't created yet. And in mathematical Platoism, it's kind of the school of thought that mathematics exists independent from human thought. And so I'd love to hear from the panel if they're more in the school of mathematics needing to be manufactured or mathematics needing to be discovered, and what real-world implications exist for us as humans, given one or the other.
I think I'll leave that to the professor here.
I think this is a great question. Just to clarify, I didn't say AI can do world-class mathematics yet. That's not the case yet. But I think we should anticipate that future. And as you may guess from whom I cited earlier, Wittgenstein has spoken extensively on this topic. And I think of mathematics as a language, as a way of interfacing with the world, and a way of creating abstractions that allow us to reason about those interfaces with the world. And so as a language, it is really invented in some sense. And I'm not sure what that means, honestly, for the rest of how we should think about discovery and so on. But I think it does tell us something about how we should think about mathematics and science in general, which is that it's really a thing that we get to create. That the concepts that we develop in part in biology and physics are defined by what exists in the world, but they're also defined by the things that we care to talk about, and that I think is important and interesting to keep in mind.
All for now. I'm sure we all have a lot more questions, but we are at the end of the hour. Thank you so much, Pat. Thank you so much, Joanne, and thanks, Nan, for your time. I really enjoyed the conversation and learned a lot, so this is check mark for the day. I can go back home, but thank you so much, everyone, and enjoy the rest of the conference.
Okay, folks, hold tight for just 5 minutes while we reset the stage in anticipation of our final fireside conversation.
Check. See, hey, check. Check. See, hey.
Okay, folks, we're now ready for the final kind of structured event in the symposium. So if you can make your way back, we would appreciate that. Okay, so let me sort of say, we had the three panels, one on funding, one on research, and one on kind of compute and infrastructure and data. And I think broadly of those three panels fitting together very nicely in the AI for science space, it's kind of like my favorite dessert, which is a baked Alaska. Okay, for those of you who don't know it, it has meringue on the outside. That's the flashy part. I think of that as the research. And then there's the ice cream inside, which is kept cool by the meringue on the outside. That's kind of like the funding side. You need that to insulate. And then you can't go anywhere without the often forgotten cake part. Okay, that's kind of the data and compute and models. And the three of them come together beautifully, I think, to make the space work. But now kind of continuing in the theme of the three panels and really bringing them all together, we're incredibly honored to have this kind of fireside conversation, although, okay, minus the fireside, with Vinod Khosla, and it's moderated by Lauren Reeder. So Lauren is a partner at Sequoia Capital. She typically invests in seed and early stage companies at the confluence of AI, data, and infrastructure. Before joining Sequoia, she was the director of product at Twilio and Segment, and was a managing partner at Graduate Fund. And I'll let her introduce Vinod and take it from here. Thank you both so much for being here. We really appreciate it.
Wonderful. Thank you for having us. Well, Vinod is a man who does not need a lot of introduction, so I'll get started shortly. But Vinod was the co-founder of Sun Microsystems, started Khosla Ventures, an early investor in so many fascinating companies. I think most top of mind for many of us is OpenAI, and has been a proponent of the forefront of technology, investing very successfully, one of the most successful investors in things that far before they are obvious. And so hoping to learn a few lessons from all of his years of betting big and getting it right. So maybe let's start with the story of OpenAI, actually. We were just chatting about this before. You invested in 2018, just when they became a nonprofit. And I think you actually had to write an apology letter to your LPs after making that investment.
Yeah, so it is true. I wrote an apology letter when making the OpenAI investment. Hello? Yeah, great. I did write an apology letter when making the OpenAI investment because there was so many things wrong and there was no plan to ever have products or revenue or anything else. And I decided I was convinced enough about the benefits of AI that it needed to be funded, and I invested twice the initial investment I'd ever made in the previous 35, 40 years of venture capital. So there was no lack of conviction in a thing, so I did apologize for it.
What did you see that gave you so much conviction at the time? Like, take us back to 2018. Transformers, barely well known.
Yeah, the Transform paper had come out, but nobody was paying attention to it. It was one of thousands of papers. There's a couple of things that are pretty important to me. First, in the general field of AI, a lot of talent was flowing in, and you want to follow the talent. It was pretty clear we were going to see that. Now, I was very, very convinced a long time ago. In fact, there's an interview with me in the New York Times in the year 2000 when I said AI will redefine what it means to be human, and I still believe that. And we are very close to that point, sort of within a decade or so. What being human means is going to be an interesting question, but I won't go there today. What was clear was talent was flowing in. What was clear was AI was going to have a huge impact. To me, it was clear. There was nothing I could think of And I'd given a talk in 2016 at the National Bureau of Economic Research. And my first slide in that talk was the 20 largest employment categories in the United States. And this was to economists, not scientists. I much rather talk to scientists. I said, I can't imagine any of these jobs not being able to be done by an AI within some reasonable time frame. That was 2016. If you believe that, then you have to believe that the timing of breakthroughs doesn't matter. If a lot of talent is going in, and you can disrupt almost every major employment category, then you should be betting on it. And shouldn't be saying, will you meet next year's plan, or will you have this breakthrough the year after? Almost impossible to predict. There was another factor. I used a set of charts in that presentation. And I'd sort of gotten frustrated with all the people who were talking about the silly things AI did back then. You know, it prescribed, ask an 83-year-old man whether they were pregnant. And that's silly, but if you looked at the improvement in capability in 20 different domains, whether it was ImageNet kinds of stuff or others, the graph was clearly exponential, but well below human performance. If you used imagination, it was almost certain the graphs would cross human capability. So I was just following the data. The data and the talent flowing in the impact it could have, it was obvious to me that we should make this investment. It was also obvious if we didn't, we wouldn't have a center of gravity for AI research in the US outside of Google. So Google was a great team, but they weren't looking at AI as a commercial large impact thing. There was Baidu in China, and I thought it was essential that the Western world have another AI effort, so that was more of a social geopolitical thing.
One of the best investments of our generation.
I hope so, though I have to say there was a similar story with TCP/IP, as odd as it sounds. In 1996, there was not one public telecommunications company, major telecommunications company that believed in TCP/IP. So I talked to all of them, and every single one I talked to said they would never use TCP/IP in the public internet. This was 1996. They were all going to use the technology, go back in the Wayback Machine and look. Every plan was to use ATM as the technology, so I started Juniper because I thought ATM wouldn't work and TCP/IP would. And again, it was the data. TCP/IP usage was expanding as an exponential. It was clear it was only technology that could scale. I had real conviction. And so I made 2,500 times our money in that investment, because I bet against the grain of what everybody else was thinking. So my one piece of advice, never listen to experts, look at the data. Expert opinion is generally pretty poor when things are going to change. It's pretty good when tomorrow's going to be the same as today. I can guarantee with reasonable certainty as an expert that tomorrow's weather will be like like today's. But that's not useful. It only matters if there was a tornado coming in tomorrow. When there's change, expert opinion doesn't count very much.
So you say you look at the people and you look at the data. If you take a survey today looking at those two things, what do you see coming next?
Well, frankly, what I see coming next, how many people here have seen a document called Situational Awareness? A few hands. Everybody should read it. I am going to guess we will see more progress in AI by the end of 2026 than we've seen in the last 5 years. This is sort of 5 years ago, Chat GPT-2 territory. We will see more progress in that. And I can't imagine by 2030 there will be any job that economically valuable job, and we can come back to non-economically valuable jobs like philosophers. I don't care about those. That humans can do that AI won't be able to do better by 2030. It may not be deployed that way. There will be lots of resistance to its use, but almost certainly that'll be true. Every expertise, and we can come back to the topic, will be free. A doctor will be free. An oncologist will be free. A structural engineer will be free. An accountant will be free. If all these things are free, what happens to the economy? So all that is really fun to speculate. I can go as deep as you want. I wrote a 25-page paper called AI Dystopia or Utopia that I refer people to. It's 25 pages. I write a lot. It's fairly detailed look at all the dystopic visions for AI and all the utopic visions for AI. But the thing why I'm excited to be here today, I think the single biggest thing that'll happen is us starting to build AI scientists. That's happening today in AI companies, AI scientists doing AI research, doing new hypotheses, writing the code to test it, testing it, and sort of coming up with a new hypothesis. So why will we have exponential progress? Because most of the AI will be done by AI scientists within a year or two. And it's starting today. But even more exciting to me is AI scientists in every other area. My bet is we'll see more scientific progress in the next 10, 15 years than we've seen in the last 150 years. Think about that. 150 years ago was 1875. And if 2040 is more progress than we've seen since 1875, it's worth thinking about. And this paper's situational awareness essentially said that there's no more than a couple of hundred people that understand this phenomena. It's very hard to internalize. It's very hard to internalize that almost every job, it's not quite as simple, but be capable of being done, whether it's being done or not, being capable of being done by an AI. You pay a farm worker the same that you pay an oncologist today? And this applies to everybody who's in medical school. They'll barely have graduated. Why are they going to medical school? So very interesting questions for society. But if AI is doing most of the research, room temperature superconductors become really quick, rapid research on. Sort of simulating the human body. 2016, I wrote about the fact that it's silly if we don't have a digital twin of every body. There's about 3,000 metabolic pathways in every body. Every drug affects multiple pathways. That's why you see each human respond differently. Why isn't there a way to test what a drug will do for me in my body with my genetics and my metabolic pathways? And a continuously evolving digital twin. That's pretty exciting. I could do that in so many areas of science. Today, how many people know transcription factors? A few hands, great. There's thousands of cell types in the body. If you're going to replace any given faulty part, your car has 5,000 parts and you can replace most of them. Your body probably has 5,000 parts you might want to replace, or cell types, if I can call them that. We know how to take a stem cell and quite accidentally and through brute force have discovered maybe 10 paths to turn it into a diabetic cell, islet cell to be more precise, or a cartilage cell for your knee replacement. We're building a transcription factor model. And by the way, there's probably 100 million wells of data in biology terms, where a well is the one experiment you do in a well, if those of you have seen a well, that need to be done to build a model for transcription factors. You can say, how do I go from a stem cell to this particular cell type, or this specific subtype of neuron? It'll be great when we do that, but AI scientists can do this pretty easily. I could go on and on. I could talk for an hour about AI and science.
What do you think most people are missing with AI and science? Like, what is underappreciated or misunderstood?
Well, nobody's even imagining AI scientists doing most of the research, which will be true in 10 or 15 years.
Missing the second order effects.
Yeah, it's so large, it's almost hard to imagine.
Where do you think the bottlenecks are from the path here to there?
I think the biggest path isn't what can be done, it's what people think can be done. So, we have two companies in fusion. We were talking about fusion earlier. They're both working with DeepMind because plasma control is a high dimensionality physics problem. Very high dimensionality physics problem. It can only be solved with sort of, you can't do a regression fit or a 5-parameter control model for this. It's a much more complex model, so something like DeepMind can do that. And as I was saying earlier, I discovered this many years ago. So before I invested in OpenAI, we had invested in a company called Atomwise. How many people know Atomwise? A few hands. So the biology guys know. And what I realized, it must have been 2014 or so, that deep learning models can do structural biology better than any PhD in structural biology. And these were structural biologists who said, oh, let me not do that, structural biology, let's just build models that can do drug discovery for me. How do I dock this small chemistry molecule to this receptor? And if you know Lee Cronin, who's mostly interested in the origins of life, he's trying to build a AI chemistry lab, and this is probably worth talking about. What does it take to build an AI chemist? You can learn all of chemistry, anything that's in textbooks or papers or all that. And once you've done that, you have no way to test your thesis. In doing our transcription factor model to say, how do you apply them? And there's millions of sequences you have to generate. That's a physical lab problem. You can't generate enough data. What we had to come up with and work with combine two developmental biologists with somebody who knew how to generate many, many orders of magnitude more data per experiment. So you can do 100 million wells worth of experiments with thousands of wells, not hundreds of millions of wells. So this nonlinear creativity was needed to close the loop of, if you apply these transcription factors, what happens? And then use the model to train on that. And I think Lee Cronin in chemistry wants to do that by being able to generate any chemical and synthesize it, which most chemicals you can imagine can't easily be synthesized. And everybody sends any chemistry they designed to Wuxi Aptec in China that has thousands of PhD chemists that try try and synthesize it, and they'll say, oh, of these 20, here's 3 we can make for you. That's a pretty dumb way and non-scalable way. I saw another thing that blew my mind. This is full complex chemical synthesis, and I won't go into the details. There are kids playing in Minecraft, synthesizing blocks in Minecraft that go directly to the robot that synthesizes that chemistry. What are kids doing? Hey, I want a blue chemical. Turns out the AI knows the length of the wavelength that replicates, hey, I really want something that's 560 nanometer wavelength. The kid only knows they want blue. And it synthesizes the blocks to do that wavelength. And if that's the wavelength the chemistry replaces that you built in Minecraft, the robot produces the right chemistry. Now, this is the beginning of saying, will a chemical have the properties you need to close the loop so you can actually develop a foundation model for chemistry? Just like we're doing in transcription or developmental biology. And that can be done in so many areas, in material science, in almost every area of science. So, sorry, I'll stop talking. I talk a lot. I get excited about these things.
It's an incredible example if even kids can help.
Yeah.
Just playing a game. One question for you is, if you were to take a year off, you've been a founder many times before, and to start your own company again, what would you do?
Look, large impact problems. I don't think medical expertise should cost any more than the cost of computing, which is declining rapidly. So all 7 billion people on the planet can probably get the best medical care, which is primary care with a built-in oncologist and a built-in gastroenterologist and a built-in endocrinologist and neurologist, for less than $1 a month. That's what I would work on. I'd make that happen. That's, by the way, I've said this publicly many times. This is a trivial problem. This is not a hard science problem like plasma control is. This is a trivial problem to do. And that's the problem just because of the scale of impact it can have. And most people in most parts of the world. I grew up in India. If you get cancer, you don't get to see an oncologist. Your primary care physician, if you happen to have one, will handle it. That's most of the people on this planet. We live in a very different world. We'll get a tumor board, God forbid if I ever get cancer. I'll get a tumor board at Memorial Sloan Kettering or something like that. Most people won't get that. And even at Stanford, if you have, say, breast cancer, and if you have triple-negative breast cancer, the oncologists you're seeing at an institution like Stanford or UCSF, pick your favorite, probably doesn't remember the last 500 articles on triple-negative breast cancer that have been published in peer review. It's silly we can't harness that knowledge today in an everyday context. And that's not a hard technical problem. There's a lot of work to be done, but it isn't hard technically. Nobody can tell me we can't do this. If you told me we can't invent a room temperature semiconductor, I might say, oh, that's a possibility. But if you tell me which paper of the 500 or 5,000 last papers on breast cancer you'd apply to my case, that's a trivially solvable problem. It's sad that we don't have it, and I'm excited that by 2035, this won't even be a question. We'll laugh at it.
What are some things that...
This is why AI is so large. This is why I believed enough to do OpenAI. I made my first deep learning investment in 2014. and that failed. But you know, failure doesn't mean it's not a good market. Failure just said you did it wrong. And there might be a right way to do it. There might not, but there might be.
Curious, actually, what are some other examples where you invested too early and maybe got it wrong the first time, but then got something right the next time?
Boy, there's so many. I like to say, in the 40 years I've done venture capital, I have failed more than almost anybody I've ever met on more things. I just hopefully don't make the same stupid mistakes again and again, and I learn. But yeah.
Learn between the first deep learning investment and OpenAI.
The value of the application mattered, for example. There wasn't enough value. It was an ImageNet kind of thing for recognition of images, and there wasn't, it was cool technology. A company called Jetpack. It just wasn't a good investment or a good application area where we could charge a lot, especially in those days when computing costs a lot more. It was a deep learning model. It wasn't a transformer model.
So there was another one, I think, called Sciencescape from a decade ago that probably is possible today.
Which one?
Sciencescape or Meta.
Mm-hmm.
I'm curious what you learned from, like, what's changed between then and now.
So this is a classic example. Anybody from CZI here? One or two names. I don't want to offend anybody at CZI. But there was a company that was looking at all the scientific literature. And I still think this is an unsolved problem today and can be done. And they had a good handle, they had good access to the articles and data and all that. And I said, why don't you work on the problem of, if I'm interested in a topic, give me all the literature on that topic and look inside and tell me all the conflicts between those papers. There is a lot of conflict in published peer-reviewed research. If you could surface all those conflicts, you'd have first 1,000 more PhD topics to research that our AI scientists can do research. But I just wanted to say, tell me all the conflicts. Where are there conflicting facts in published literature? But then CZI bought this effort and turned it into something that, as far as I can tell, didn't amount to much. But being able to research literature and say, tell me where things agree or disagree, actually gives you the most promising avenues for new exploration. It happens where there's disagreement. So that was an effort a long time ago. But we never got to fund it because CZI bought the company.
I think it's a fascinating one. It would be very useful to have today.
It would be hugely useful. Look, if Pfizer's or a pharma company is researching a receptor, they commission these studies. And 100 people will work on it to say everything about that piece of science. Get it to me, and then we'll have our scientists work on it. These research studies could be done in 15 seconds.
I'm curious to turn a little bit personal, to learn a little bit what makes you, you, and how you see the world this way.
Just being an optimist. Hopefully that came across.
Well, you post these 4 very interesting facts on your website. One is your age. 2, that you've been married to your childhood love for 50 years. 3 is that you were twice rejected from Stanford's MBA program.
Yeah.
And then 4 is that the hardest thing is staying relevant to young entrepreneurs. Why did you pick these 4 to help people get to know you? And what else should we know?
Well, first, there's some things that are really important. I've been, in fact, tomorrow is the 54th anniversary of my first date with my wife. So I'm excited for it. And by the way, part of it is I care much more about our first date than our wedding date, because wedding is just protocol along the way. First date is what counts to me. Yeah. So that was one. And by the way, I live in the same house since 1986. So there's an element that's super stable. And in '86, I decided I would build a house, and I turned 70 a few months ago. I was age 30, and I decided I'd build a house I'd live in for the rest of my life. And I wrote a spec for it like no architect had seen, what it'd be like when I was, so I break things down. I'm a first principles thinker.
What was in that spec?
Exactly how we want to live in our 30s, our 40s, our 50s, our 60s, and our 70s. I actually made the mistake of not looking past the 70s. It seemed far away when I was 30. And then I realized recently that I hadn't thought through my 80s. So I went back, and the only time I've done anything to the house is made sure that if I was in a wheelchair, like last year while on a ski trip, I fractured my hip. And I said, oh shit, I actually can't take my own showers. I'm in a wheelchair. And so I went back and re-equipped the house for wheelchairs and all that other stuff for my 80s, 90s. And hopefully I can work as long as Warren Buffett, which gives me another 25 years of productive work. And then nobody will need to work long before I'm done working. So that's my current plan.
That's amazing.
But that was the reason that 50-year thing
was important.
And being in the same house is important. What were the other facts?
Staying relevant for young entrepreneurs.
I'm sorry?
Staying relevant for young entrepreneurs.
The second thing is
the
important.
hardest thing.
I got rejected at Stanford twice. Yes. Now, I always took the view that they were making a mistake. I wasn't not qualified to get in. But I'm never embarrassed by any facts. I'm always trying to do better. And if you don't admit where something might be embarrassing, you're not going to confront it directly. And so it's really important, and I say this to entrepreneurs, spend more time figuring out what's wrong with your company than what's right. Because if you discover those things early and aren't embarrassed to talk about what might fail or where you have hidden doubts or other things, then everybody does. If you discuss it explicitly, you'll find a way to solve it. If you discover it late, you may not have time to solve it. So very important to surface what's wrong. And I used to tell my son, you know my son, I used to say, if I praise you, you just feel good. There's nothing to do about it. If I tell you what you're doing wrong, you can do something about it. It's actionable. So critique is really, really valuable. So, and that relates to the last fact. You know, most of the creative ideas come from younger people because they're less constrained. And I'll tell you a fun story. They're less constrained. But then I can say I'm successful, and sort of they can come to my office, and I'll sit across a desk and listen to them. By the way, I eliminated the desk in my office a long time ago, because when I'm sitting at a desk, I want to be more approachable. So there's no chair or desk between me and the person talking to me. Little dynamic. You want them to feel like you're equal and speak up. And you learn a lot from people who will freely talk to you versus people who think you're somehow higher in the hierarchy and they can't openly express their concerns, opinions, whatever. So it's really important to get contrarian opinions. I spend really hard to be, one, relevant, see how younger people are thinking, and to learn from them. So most of my learning comes from people who come in to talk to me. And so young people have the freshest ideas. The fun story, and this idea of thinking out of the box is not restricted to young people. Anybody can do it. But once we know a lot, once we get to be expert in an area, we have too many biases that say we'll extrapolate the past into the future. The phrase I hate the most in entrepreneurship is we've been doing this for 20 years. Almost certainly then you're speaking from experience, not from first principles thinking. So it's really important you encourage first principles thinking. So I was invited to do a dinner talk by the director of the Lawrence Berkeley Lab. And they had, I was the dinner speaker, they had the heads of each of their departments, and my first question was, how do we increase the level of innovation at Lawrence Berkeley Labs? And my answer was simple, and to this day, they didn't do it, but I believe it. I said, your head of nuclear is clearly a smart guy to be head of nuclear at an esteemed institution. Your head of whatever, physics is a smart person. Your head of biology or chemistry is smart people. But they've been in their jobs too long. So make the head of nuclear head of chemistry, make the head of chemistry head of biology, shuffle the roles so they are forced to think from first principles in a new area, because they clearly have the IQ, but they have too many biases about what is possible or not possible. And so that's really the key to why I focus on all these. These are pretty important facts.
It makes a lot of sense.
Makes a lot of sense after I explain it.
When you put it that way.
You're probably wondering, why is these silly facts on?
Correct. I have one last question, then we'll turn it over to the audience. So you've given a lot of predictions related to AI. What is your craziest 10-year non-AI prediction?
So I have a TED Talk I did last year, and I did a version of it, a better version of it, at our CEO Summit last year, called Implausible Tomorrows. So Google my name and this talk called Implausible Tomorrows. I have a dozen forecasts for the planet. Every single one, when I talk to experts, they say, that's silly, that's not gonna happen. I can't think of a single reason why any of these might not happen. So let me tell you the simplest one. I think by 2050, we will have replaced most cars in most cities. How many people have thought about that? One or two hands, that's good. I fundamentally believe there's a much superior system to cars, which is a version of public transit, but doesn't look anything like my current public transit. It's public transit on demand in self-driving little pods. Turns out it's the only way you can 10x the throughput of passengers per hour through any street. The only way. Every other way, including Waymo or Uber, increases congestion and reduces throughput. And if our city is going to be more vibrant, you have to 10x. You can't destroy the buildings on both sides of a street, so street width is the only constant. If you sort of say, how do I 10x the throughput? And so there's one answer, and I won't go into it for the interest of time. But I started with a simple metric. How do we do 10x the throughput of any given street width, per foot, per meter? Then I said, what's the easiest way to get this adapted? It's to build it in the width of a bicycle lane. So we can build more capacity in a bicycle lane than a light rail system using this public transit system. And everybody thought I was crazy. By the way, OpenAI was 2018. At the same time, same year, we invested in Fusion, Commonwealth Fusion, because I'd run into Bob Mumgard, who was a senior fellow at the MIT Plasma Fusion Lab. I love hanging out at research labs, so I learn a lot. And we did this public transit thing.
That's amazing. All right, let's open up to...
And I want to make one point. Whatever area you're in, what you think is possible is limited not by what's possible, but by your thinking about what's possible, and you start putting constraints on it. As soon as I said public transit, people said to me, that's silly. People won't give up cars. Well, they won't give up cars if a car is more convenient. In our system, every trip is always provably faster in our public transit system. It's provably cheaper, even then compared to a chauffeur-driven car, it's faster. And I can go through the math of it. It's a simple problem.
Thank you.
Oh, I don't know. Okay, it works. Yeah.
Put it closer to you.
Yes, absolutely. So I have this belief that all the industries that are successful, the companies that are successful, are actually following mega trends and something like gravity, something that is inescapable. For example, for AI, there is no putting the genie back in the bottle, or for example, storage of electricity in lithium batteries. There is no going back from that. And it might not be lithium, but it's going to be electricity. So what do you see that is emerging as a mega trend, as gravity, apart from AI, or complementary to AI?
Well, so beyond, first, I think it goes beyond mega trends. Almost every implausible thing was possible, but wasn't happening because somebody wasn't doing it. So the other thing I hate is when somebody says to me, they should do this, X or Y, and I say, why aren't you doing it? There's no they in the word. But to directly answer your question, obviously AI, but beyond that, energy. The consumption of electricity or energy per human has gone up. Used to be restricted to the food you could harvest and eat. Now it's motors and oil to run engines for you, things like that. And hopefully soon AI. But amount of energy we can produce, and this is why I have a strong interest in fusion, can be scaled, but would not have happened. I guarantee you wouldn't have happened if Mumgard hadn't said, I have this design for a reactor which is based on the idea that high temperature superconductors are possible now. And so we can build a 20 Tesla magnet. And because we can build a 20 Tesla magnet, the size of the magnet goes down to the 4th power. So you 4x the power of a magnet, say from 5 Tesla to 20 Tesla, it's 256 precisely times smaller as a device. And suddenly it becomes feasible to think about these things. It's no longer a 50-year project. It's no longer $50 billion to prove it out. It's doable. But one person had to decide to go do it. All the automakers in the world couldn't build an electric car till Elon decided to go build an electric car. So it's some entrepreneur trying to say, I'm going to make this happen. I'm going to make every physician expertise free on the planet. Which, by the way, I'm having my son work on. I have 10 other problems I'm working on, but this is all exciting.
The blue shirt? Oh, the woman in the back.
What will it mean to be a human after 2035, and how can we build ourselves up for it?
So we have our annual CEO summit, and I'm going to give a talk there next week, so it'll be available publicly. It is partially covered in my paper from November 2024 on AI dystopia or utopia. If nobody needs to work, and the narrow-minded people say, well, how will people find meaning? They forget that most jobs on the planet, even in this country, most jobs are servitude, they're not jobs. If you work as a farm worker for 40 years, for 8 hours a day in 100-degree heat, it's not a job. It's not something I would call a job. It's servitude necessity. Same thing with any assembly line worker at General Motors. So AI will free humans to be humans. You won't have a 5-year-old kid entering kindergarten being told, if you study hard, you'll get a job. You can finally say, pursue your passion. If you want to be an artist, your basics and necessities in life will be taken care of. If I want to be the fastest 100-meter sprinter, I can spend my life trying to do that. Or if I want to be the best surfer, or the most competitive at something, or the best garden I want to create. By the way, ChatGPT is great for designing gardens. I do it every time. You can literally tell it sun exposure of every plant that you have, what size plants, what color you want in early spring, late spring. It goes through and what USDA zone you live in. It figures all this out and can design you a garden that's beautiful flowers all year round. So the possibilities, I could just see gardening, for example, for myself. Right? I love gardening. And I use it explicitly to design my garden, which I still spend time on. You know, the number of times I say to my wife, I love the feeling of this garden because every month it's been different and really colorful. That's what it means to be human. Or take all the time looking after your children, not feeling like you have to leave a 16-week-old baby and go to work. Think about that. Or you can look after your parents. Actually take the time, or take the time for a relationship. So whether it's being an artist, a musician, gardening, whether it's useful to others or not, that's what it means to be human, and that's what AI will enable.
I think you have a very beautiful garden in your office, in fact.
Oh, yes, I designed the garden in my office too.
So I'd like to ask a question from the perspective of experimental scientist, previously physics, now neurotechnology. And of course, everyone is wondering whether we lose our jobs sooner or later. You're saying that AI will replace all of the jobs. But specifically, we are talking a lot about AI, but for experimental science, what's crucial is an interface to experiments via often sophisticated apparatus. Here, microscopy or colliders, accelerators, and so on, and which requires very sophisticated access to matter, physics, biology, and so on. So what's your take on evolution of science while AI is so much not only emerging but just galloping, and the role of robotics? Because I don't see a clear pathway where this part of some cutting-edge technology that are experimental are replaced without robotics, and even with robotics, seems that we are still needed.
So that's the point I was trying to give you about to build an AI chemist. You need to synthesize chemistry to build a foundation model. Millions of compounds. And so we have to come up with clever ways to close the loop in science between a theoretical design with an AI to actual synthesis of chemistry or a recipe for transcription factors to differentiate a stem cell into a particular type of cell. In science, physical things have to happen. And I think in many areas, I'm seeing very, very creative approaches. In transcription factors, can you run 1 million experiments in one experiment, for example? So you can do the one experiment, but you get 1 million data points to develop your model further. And experimental physics will be similar. I will say the following. I still work 80 hours a week easily. Why at age 70 when I don't have to work for a living or need to make more money? I can't spend the money I have in my lifetime, neither can my kids. Why am I working? I have an addiction to learning in addition to gardening. And so humans will learn for the purpose of learning. And the best experts in each area come pitch me how they're going to do X or Y. Whether it's a new approach to transcription factors or stem cell differentiation or some other area. And I do think the physical part will be needed for a bit, and robots will make it easy. So I do think you don't need humans to run experiments. And already you have not only robots to do things the way humans do it, but new ways to do it which are designed for the experiment, not for the human to do it. So most of the science world is designed around experiments humans can do in the human form factor. That's why human form factor robots will be the way to replace exactly that, but there'll be new ways to do it, like barcoding in genetics can run hundreds, thousands of experiments in one. You know, people are trying to design LNPs to deliver gene therapy. There was this fabulous example of gene therapy recently. Well, we have a way to run 10,000 LNP experiments in one primate experiment. We have breakthrough in a company called Liberate to do that. So you will find new ways to do it versus the human way to do it. If you had 2 arms and 2 legs and 2 eyes, how would you do it? So there will be creativity there too. But I do think lots of people will actually not stop working. They'll work on what they want to work on when they want to work on, not because they need to work like a farm worker. I think hopefully we can eliminate all the undesirable jobs on the planet. And people will, I work because I want to work, because I want to learn.
Thank you so much, Dmitry Starson.
Sorry, I get passionate about all these topics.
So one of the topics you are obviously very passionate about is fusion, and I wanted to ask kind of 3 related questions to the topic. First, the overarching question is the timeline. What do you see the timeline for reaching
Before
fusion?
2030.
Before
2030.
You build, okay.
One of my predictions, I was talking about my TED Talk, I believe we can replace every coal boiler and natural gas boiler in this country with a fusion boiler and be completely done with fossil fuels in existing power plants, retrofit them in the 2040s.
And do you see this as a solve? And do you see this as a solved problem with Commonwealth fusion basically being the winner take all, or do you see other opportunities for other newcomers in that space?
Yeah, I'm not predicting Commonwealth fusion will be successful. I recently had 3 different expert teams in fusion from 3 different fusion labs, diligence Commonwealth fusion, and I asked a single question. By 2027, will positive energy, which is the key metric in fusion, you produce more energy than you put in, be proven? What is the risk? And the answer was very small. From all 3 different independent labs that didn't know what the work each was doing. Gives me high confidence that they'll get to positive fusion sometime. Whether that's off by a year or 2, I don't really care. But what's even more important is because Bob Mumgard started Commonwealth fusion, there's a dozen other credible efforts. And when you have that many and they're different and trying different things, it'll get solved. I think today it would be faster to start, and there's new efforts, there are credible efforts other than Commonwealth fusion. It'll be easier to start a new effort, like Pacific Fusion, for example, and Eric Lander is a good friend of mine, and develop the reactor. Then to permit one nuclear fission plant, because it'll be tied up in lawsuits because nobody wants a fission reactor in their neighborhood or anywhere near their city. So it takes longer to go through the legal morass of permitting than to design a new fusion reactor today, especially if you use AI to do some of these things.
Thank you, Lauren. Thank you, Vinod, for the wonderful talk. I have a slightly more philosophical question. You just mentioned that wisdom and experience could be a double-edged sword for entrepreneurs. I think my question would be like, can AGI replace that part of, I would say, like building companies, and humans like love quality of richness and experience about their consciousness. So can AGI, like, what would that be like? How would humans feel about it?
That's self-evident given the definition of AGI. They can do anything humans can, and hence it can replace humans in entrepreneurship or venture capital, for example. Yeah. In fact, I think in the next 5 years, we will see a company with $1 billion in revenue and less than 10 employees. Almost certainly we'll see that. They'll use AI accountants, AI salespeople, AI scientists, AI software developers. Almost certainly in the next 5 years, we'll start to see that company.
All right, last question.
Hey, hello. Hey, thank you for a nice talk and question and answer. If you think that in the future, because of AI, people won't have to work anymore and they'll have these nice opportunities to focus on what they want to and learn what they want to, how do you think the advertising industry is going to change in response to that? Right now, people are little micro allocators of their own capital, and there's this attention economy that's trying to, perhaps keep you focused on one thing instead of another. So will that be enhanced or illuminated, or how will that change when people don't have to work and capital is allocated very differently?
So, talking about advertising in this world is like talking about how we should rearrange deck chairs on the Titanic. It's largely irrelevant question. But you said something else that was important. You used the word attention. And I think the attention economy ties back to humanness. What is humanness? Humans will be humans. They'll care about status. They'll care about celebritydom. They will care about getting attention. And so there's a couple of books now on the attention economy, which is what I figure you're referring to. Attention is a human characteristic, like status is, like caring is. Those we will have much more ability to pursue because the human brain won't get rewired. Evolution doesn't happen that quickly as fast as AI evolves. So people will still seek attention. That's what the influencer economy is about. That's why, Trump got elected. He got attention. Good or bad didn't matter. He was able to convey a set of ideas because of the attention economy. So I do think human characteristics will stay human and human brains won't change. So AI will have to serve human characteristics, include good and bad. Hopefully not too many of the bad things. But I do believe in a world where Facebook can hack any brain, by changing the shade of blue in an ad, get you to be more likely to click on it. That's the advertising economy. Every human being will also have a personal AI agent that fights the marketeers. So advertising will have to become more about information than about convincing people to buy stuff they don't want to buy. have no intention to buy, which is what advertising has become, making you want things you didn't know you wanted. And that's a bad part of the advertising economy and the capitalist system. I could go on forever on that. We'll take one last question. This lady
yes,
had
this woman had one more.
a hand up.
Oh my gosh, awesome, thank you. So clearly you're very introspective. You've even kind of planned your vision of your life. What's something you thought we would have by now, and why don't we have it?
Clearly, we should have much better medicine. A lot of medicine is driven by, and this is I love the capitalist system, but it's driven by the disadvantages of the capitalist system. Take a simple example. Anybody heard of the poly pill? Google it. It's a combination of things like aspirin and stuff. It would do more for human health than any other single thing, but nobody's ever run, there are plenty of academic papers saying why it would be beneficial, but nobody's run a trial to get an FDA approval for a poly pill because it's not patentable. Because it's not patentable, there's 100 examples like this. Nobody will run a trial. Rapamycin, for those of you interested in longevity, likely very useful for extending health span. Nobody will run a trial because it's not patentable. There's a few efforts at creating variants of rapamycin that are patentable, but that's a silly thing to do when we have rapamycin. So lots of things like that should exist, don't for reasons that they don't have economic motivation behind them. One of my favorites, and this is a good place to end, my wife's working on it. Every child on the planet today should have a personal AI tutor. I like to joke, I have the largest personal AWS bill because we fund an AI tutor. All STEM content for K through 12 education is free on CK12. And there's probably 5 million kids a month using an AI tutor. It costs less than $1 a month. Get a personal tutor for every kid that can immediately say, where are the gaps in your knowledge? If you're trying to understand this concept, here's the 3 things you have weakness in. You can figure this out in half an hour with a kid. What are your gaps in knowledge? What do you have to learn before you learn this new thing? And how you can prepare for your exam better, which is the question these kids are asking, help with homework or preparing for an exam. But that every kid should have today. It's available for free. I don't think I could fund it if it was 500 million kids using it, but 5 million is pretty easy to handle. So, free AI tutors to everybody and free primary care, 2 things that should exist today. Thank you all very much.
Thank you, Vinod.
Okay, thank you so much, Vinod and Lauren. That was, okay, at least for me, very inspiring and interesting discussion. It's really a pleasure to have both of you. So let me just say in closing, today's symposium, I think, for me, and I hope for everyone here in the crowd, has been a source of both information and inspiration. Certainly, I'm going to try to rethink the rest of my life. I'll plan for my 60s and 70s and 80s, maybe 120s. I'm actually even more of an optimist than Vinod was. You know, I think accelerating the rate of scientific progress in general is one of the great challenges that we face today. I think that's why so many people came out. So on behalf of Foundry and our co-sponsors, Invisible Technologies, Open Athena, and Enigma Project, we'd like to thank you all for coming. In particular, thank all the panelists and all the poster presenters, all the staff here at Terra Gallery, and so on. And so we invite you to a happy hour where we can discuss what we learned and maybe learn some more from the posters. So yeah, thank you again.